Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight, ready to let the day fade and settle into something quieter, something that invites wonder without demanding answers. Tonight, we're exploring a question that seems simple at first, but opens into layers upon layers of mystery. How many dimensions does the universe actually have? It's the kind of question a child might ask while looking at their hands, noticing they can move up and down, left and right, forward and back, 3 directions, 3 dimensions. It feels complete, doesn't it? Like that's all there is, all there needs to be. But physics has been whispering for over a century that reality might be hiding more, that beyond the 3 dimensions we navigate every day, beyond even time as a fourth, there could be directions we've never turned toward. Space is folded so tightly we've never noticed them. Dimensions that don't reveal themselves to our senses but show up in equations in the mathematics that describes the deepest structures of the cosmos. Before we begin this gentle exploration, I'd like to know, where are you right now? Can you see the walls around you, the ceiling above, the floor beneath? These boundaries define your 3-dimensional space. But what if, at every point in your room, there were additional directions curled up so small that not even the finest microscope could detect them? What if reality has secret corridors running through every atom, every photon, every moment? That possibility, strange as it sounds, is taken seriously by some of the greatest minds in physics. Not because they want to complicate things, but because the mathematics of the universe seems to demand it. If you find this kind of contemplative science helpful, if it gives your mind something to rest on as you drift towards sleep, a gentle like or subscription helps this quiet corner find others who might need it. For those already here, thank you. You're part of this nocturnal constellation of curious minds. Tonight's journey won't give you a single, definitive answer, because the truth is, physicists themselves don't agree. Some say 4 dimensions, 3 of space and 1 of time. Others say 10 or 11, or that the number changes depending on how closely you look. Still others suggest that dimensions themselves might not be fundamental, but emergent, arising from something deeper. What we'll do instead is wander through the landscape of ideas, from the familiar 3 dimensions to the strange geometries of string theory, from Einstein's curved spacetime to the possibility that reality is holographic, projected from hidden boundaries. We'll move slowly. We'll pause often. And we'll remember that not knowing everything is not a failure, it's an invitation to wonder. So, take a breath, settle where you are, and imagine for a moment that the space you occupy is richer than it appears. That beneath the surface of ordinary experience, the universe is woven from dimensions you've never sensed, but that shape everything you know. That's where our journey begins. In the gap between what we see and what might be there. In the quiet recognition that reality could be far stranger, far more layered than common sense suggests. Let's explore together, gently, curiously, with the understanding that the question itself is more important than any single answer. Welcome to the mystery of dimensions. Stand up, if you're able, and reach your arm out to the side. Now move it forward. Now lift it up. 3 movements, 3 directions, 3 dimensions of space. This is so fundamental to your experience that you probably never think about it. Your body evolved to navigate these 3 axes. Your brain constructs a mental map of the world using length, width, and height. Every building, every landscape, every object exists within this 3-dimensional framework. But here's the hook, the thing that draws us into tonight's exploration. Physicists aren't sure these 3 dimensions are all that exist. Not because they're speculating wildly, not because they've lost touch with reality, but because when they try to describe the fundamental forces of nature, gravity, electromagnetism, the forces that hold atoms together, the mathematics refuses to work unless additional dimensions are included. It's as if the universe is a puzzle, and the pieces we can see only fit together when we acknowledge pieces we cannot see. This isn't new. The idea of hidden dimensions has been around for over a century, but it's also not settled science. Some physicists believe extra dimensions are real and essential. Others think they're mathematical artifacts, useful for calculations but not physical. Still others argue that dimensions themselves might be emergent, not fundamental features of reality at all. The question cuts to the heart of what we mean by real. Is a dimension real if it's too small to detect? Is it real if it only shows up in equations? Is it real if our entire observable universe could be confined to a slice of a larger dimensional space we can never access? These aren't idle philosophical musings. They connect to concrete mysteries. Why is gravity so much weaker than other forces? What happened in the first moments after the Big Bang? What is dark matter? What is dark energy? Could there be parallel universes? Extra dimensions offer potential answers to all of these questions. Consider this. The electromagnetic force between two protons is about 10 to the 36 times stronger than their gravitational attraction. That's a trillion times stronger. Why such a dramatic difference? One possibility is that gravity isn't inherently weak. Instead, it might be diluted because it spreads into dimensions we can't access. While electromagnetism stays confined to our three-dimensional space, gravity leaks into additional dimensions, making it appear feeble from our perspective. Or consider the unification of forces. At high energies, the electromagnetic force and the weak nuclear force merge into a single electroweak force. Physicists suspect that at even higher energies, all forces might unify, but the mathematics only works smoothly if those unification happens in more than 4 dimensions. String theory, one of the leading candidates for a theory of everything, requires 10 dimensions. Not 4, not 6, 10. 9 of space and 1 of time. Try to formulate string theory in fewer dimensions, and the equations produce nonsense infinities, contradictions, violations of fundamental principles. M theory, which unifies different versions of string theory, requires 11 dimensions. Membranes of various dimensionalities float in this 11-dimensional space, and our entire observable universe might be one such membrane. These aren't decorative additions. They're structural necessities. Without the extra dimensions, the theories collapse. But if 7 extra dimensions exist, beyond the 3 we know, where are they? The standard answer is compactification. The extra dimensions are curled up, folded into shapes so tiny that we can't perceive them. Imagine a garden hose viewed from far away. It looks one-dimensional, just a line. But an ant crawling on its surface knows there's also a circular dimension wrapped around the hose. The extra dimensions of the universe might be like that circular dimension, real but curled up at scales far smaller than atoms. How small? About 10 to the minus 35 meters. That's the Planck length, the scale at which quantum effects on space-time itself become important. At that scale, our familiar notions of smooth, continuous space break down. Dimensions might not even have clear meaning there. This is the hook that draws us in, the possibility that reality is constructed from more than we can see, that every point in space might contain hidden corridors, that the universe's true architecture might be far richer than our three-dimensional experience suggests. And the hook tightens when we realize this isn't just speculation. These ideas emerge from attempts to reconcile our two great physical theories. General relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes the behavior of particles at the smallest scales. These theories are each spectacularly successful in their domains, but they're fundamentally incompatible. Relativity treats space-time as smooth and continuous. Quantum mechanics insists that at small scales, everything fluctuates and becomes uncertain. Bring them together, and you get nonsense. Extra dimensions offer a potential way forward. They provide room for new structures, strings, brains, quantum geometries that might bridge the gap. So, the question, how many dimensions does the universe have? Isn't idle curiosity. It's central to understanding what the universe is made of, how it began, and how its fundamental forces work. Tonight, we're going to explore that question from many angles. We'll start with the 3 dimensions we know, then add time as a fourth. We'll see how spacetime curves and why that matters. We'll venture into the mathematics of extra dimensions, the strange shapes they might take, and the ways physicists are trying to detect them. We'll confront the possibility that dimensions aren't fundamental at all, but emergent patterns that arise from deeper structures of information and quantum entanglement. And we'll end where we began, in wonder. Because regardless of how many dimensions the universe actually has, the fact that we can ask the question, that we can build mathematical frameworks to explore it, that we can design experiments to test it, that capacity for inquiry is itself remarkable. You don't need to solve the mystery to appreciate it. You don't need to understand every equation to feel the weight of the question. All you need is curiosity and the willingness to let your mind wander into spaces that don't fit comfortably into everyday experience. So settle in, let the familiar 3 dimensions anchor you, and then let your imagination stretch beyond them into the hidden architecture that might underlie everything you know. The hook is set. The question is open. How many dimensions does the universe actually have? Let's find out together. The beauty of this question is that it doesn't demand you choose sides. You don't have to believe in extra dimensions or reject them. You can hold the possibility lightly, like a question mark suspended in your mind. Because that's what physics does at its best. It holds questions open, tests them carefully, and follows where the evidence leads. Right now, the evidence is ambiguous. Extra dimensions haven't been directly detected, but they haven't been ruled out either. They remain a live possibility, hovering in that fertile space between speculation and confirmation. And that space, that not knowing, is where discovery lives, where breakthroughs wait, where the next revolution in our understanding might be taking shape. So as you drift tonight, as your thoughts slow and soften, let this question rest in the background. How many dimensions? Not demanding an answer, just present, like the hum of existence itself, a reminder that reality is deeper than surfaces, that the universe rewards those who look beyond the obvious, and that sometimes the most profound truths are the ones we can't see but can only infer from the patterns they leave behind. The dimensions we know are real, the dimensions we suspect might also be real, and the gap between the two is where tonight's journey unfolds. Before we can venture into hidden dimensions, we need to appreciate the ones we already have. The 3 spatial dimensions aren't just background scenery. They're the stage on which all of existence plays out, and they're far more remarkable than they might seem. Think about where you are right now. You can move left or right. That's one dimension, often called the x-axis in mathematics. You can move forward or backward. That's a second dimension, the y-axis. And you can move up or down, the z-axis. 3 directions, perpendicular to each other, defining a framework that contains everything you can touch or see. These 3 dimensions aren't arbitrary. They're woven into the fabric of physical law. The way light spreads, the way gravity weakens with distance, the way atoms bond to form molecules, all of these phenomena depend critically on there being exactly 3 spatial dimensions. Consider gravity. In our 3-dimensional space, gravity follows an inverse square law. Double the distance from a massive object, and the gravitational force decreases by a factor of 4. This is because gravitational influence spreads outward through 3-dimensional space like light from a bulb, and the area of a sphere increases as the square of its radius. If space had 4 dimensions instead of 3, gravity would follow an inverse cube law. Double the distance, and the force would decrease by a factor of 8. This might sound like a small difference, but it would have enormous consequences. Planetary orbits would be unstable. Earth would either spiral into the sun or drift away into the cold of space. Solar systems, as we know them, couldn't exist. The same applies to atoms. The electromagnetic force that binds electrons to nuclei also follows an inverse square law in 3 dimensions. In 4 spatial dimensions, atoms wouldn't form stable structures. The delicate balance that allows chemistry to happen, that allows molecules to build proteins, that allows life to emerge depends on 3 dimensions. Not more, not fewer. Paul Ehrenfest, a physicist and close friend of Einstein, studied this question in the 1910 seconds. He showed mathematically that stable planetary orbits and stable atoms are only possible in spaces with an odd number of spatial dimensions, and that 3 dimensions offer unique advantages. In 1 dimension, complexity is severely limited. In 5 or more, the forces that bind matter become too weak or too unstable. 3 dimensions seem to be the Goldilocks number, not too few, not too many, but just right for the kind of complex, stable structures that make life possible. But why do we perceive 3 dimensions so clearly? The answer lies in how our senses and brains evolved. Vision, for instance, gives us depth perception by comparing the slightly different images from our 2 eyes. This stereoscopic vision evolved to navigate 3-dimensional environments, to judge distances, to predators, to gauge the height of a cliff, to reach for fruit on a branch. Touch reinforces this 3-dimensional framework. When you pick up an object, you feel its length, width, and thickness. Your proprioception, your sense of where your body is in space, operates in 3 dimensions. You know instinctively that to reach something above you, you move up. To avoid something behind you, you turn around. Our entire kinesthetic sense is calibrated to 3 spatial dimensions. We don't have a sense for moving in a 4th spatial direction because, as far as we can tell, that direction doesn't exist at scales we can perceive. Mathematically, 3 dimensions offer richness that lower dimensions can't match. In 1 dimension, you can only move along a line. Interactions are severely constrained. In 2 dimensions, you gain much more freedom: surfaces, shapes, the beginning of complex geometry. But you're still limited. A 2-dimensional creature couldn't have a digestive tract that goes all the way through its body without splitting it in half. 3 dimensions solve these problems. They provide enough room for complex structures without introducing the instabilities that higher dimensions would bring. But there's something subtle worth noticing. The 3 dimensions of space feel democratic, equal. You can rotate an object so that what was width becomes height, what was height becomes depth. The 3 dimensions are interchangeable through rotation. This symmetry is beautiful and fundamental. It tells us that space itself has no preferred direction, that the laws of physics are the same whether you're oriented north, south, up, or down. This rotational symmetry is so ingrained in our experience that we rarely think about it. But it's a profound feature of 3-dimensional space. In 4 or more dimensions, the symmetries become richer and more complex. Objects can rotate in ways we can't visualize. A 4-dimensional sphere can be turned inside out without breaking its surface, something impossible in 3 dimensions. Artists have long been fascinated by the constraints of 3 dimensions. Painters create the illusion of depth on flat canvases using perspective. Sculptors work with volume, mass, and the play of light across surfaces. Architects design buildings that occupy 3-dimensional space while considering how people move through them. Even our language reflects 3-dimensionality. We talk about high and low, wide and narrow, deep and shallow. We use spatial metaphors, constantly feeling up or down, being close to someone emotionally, thinking outside the box. Our conceptual frameworks are built on spatial intuitions that assume 3 dimensions. Yet, despite how natural 3 dimensions feel, humans have imagined spaces with different dimensionalities for centuries. Edwin Abbott's 1884 novella Flatland describes a 2-dimensional world where beings are geometric shapes moving across a plane. The story explores how a 2-dimensional creature might struggle to comprehend 3 dimensions, just as we might struggle to comprehend a 4th. When a sphere passes through Flatland, the 2-dimensional inhabitants see it as a circle that appears from nowhere, grows larger, then shrinks and vanishes. They can't perceive the sphere's 3rd dimension, directly only its intersection with their plane. This analogy helps us imagine how higher dimensions might exist without being visible to us. Mathematicians have gone further, defining spaces with 4, 5, or any number of dimensions. These higher dimensional spaces are just as mathematically consistent as 3-dimensional space. You can define distances, angles, volumes. You can do geometry, solve equations, describe shapes. In 4 spatial dimensions, there's a 4-dimensional analogue of a cube called a tesseract or hypercube. It has 16 vertices, compared to a cube's 8, 32 edges, compared to 12, 24 square faces, compared to 6, and 8 cubic cells compared to a cube's single interior. We can't build a tesseract in our 3-dimensional space, but we can project it, creating shadow-like representations that hint at its structure. This mathematical flexibility is important. It shows that there's nothing logically inconsistent about higher dimensions. They're not physical, impossibilities, or mathematical paradoxes. They're extensions of familiar geometry into realms our senses can't access. But for all this mathematical freedom, we keep coming back to the stubborn fact. We perceive 3 spatial dimensions, and those 3 seem to be all we need to describe the world around us. Every experiment, every observation, every measurement fits comfortably into a 3-dimensional framework, plus time, which we'll discuss next. The 3 dimensions we know are sufficient for building galaxies, igniting stars, forming planets, evolving life, and giving rise to consciousness. They're enough for everything we've ever experienced or detected. So why would anyone think there are more? The answer lies not in what we observe directly, but in what happens when we try to understand the observations more deeply. When physicists write equations to describe fundamental forces, when they try to unify gravity with quantum mechanics, when they calculate what should have happened in the first moments after the Big Bang, that's when 3 dimensions start to feel insufficient. The mathematics begins to whisper, there's more. The equations refuse to balance unless additional dimensions are added. The forces don't unify, the infinities don't cancel, the theories don't work. And so physicists, following the mathematics wherever it leads, began to wonder whether our 3-dimensional experience is the whole story, or just the part we can perceive, like the 2-dimensional inhabitants of Flatland, confident in their plane, unaware of the vast 3-dimensional space surrounding them. The 3 dimensions we know are real, solid, inescapable, but they might not be alone, and understanding why that might be true requires us to take the next step, adding time to the picture, and seeing how space and time together form something richer and stranger than either one alone. The 3 dimensions of space are also profoundly democratic in another sense. They're the same everywhere. The geometry that governs a room in your house is the same geometry that governs interstellar space, the interior of stars, the gaps between galaxies. This universality is what makes physics possible. We can discover laws here on Earth and trust they apply across the cosmos. That trust rests on the assumption that space itself, its dimensionality, its structure, is consistent. And so far, that assumption has never been violated. Everywhere we look, space behaves 3-dimensionally. Stars orbit in ellipses, not impossible curves. Light spreads in expanding spheres, not strange geometries. Gravity weakens with distance according to the inverse square law, just as it should in 3 dimensions. This constancy is both reassuring and puzzling. Reassuring because it means the universe is comprehensible. That patterns we discover locally apply universally. Puzzling because if extra dimensions exist, they hide themselves perfectly, leaving no trace in ordinary experience. The 3 we know stand as monuments to stability, to the success of physics as we've built it. And yet, as we'll see, they might be only part of the story. For most of human history, time was treated as something separate from space. Space was the stage vast, static, 3-dimensional. Time was the clock ticking in the background, flowing steadily, the same for everyone everywhere. Isaac Newton enshrined this view in his laws of motion. Time, in Newton's framework, was absolute. A second on Earth was a second on Jupiter, a second in a distant galaxy. Clocks might run at different rates due to mechanical imperfections, but true time, mathematical time, the time that appeared in equations, flowed uniformly throughout the universe. This made intuitive sense. When you describe where something is, you give 3 coordinates. How far left or right, how far forward or back, how far up or down. When you describe when something happens, you give one additional number, the time. 4 numbers total, but they seemed fundamentally different in kind. Space was space, time was time. But in 1905, Albert Einstein shattered this clean separation. In his special theory of relativity, he showed that space and time are not independent. They're woven together into a single fabric called spacetime. What one observer measures as a distance in space, another observer moving at high speed might measure as a mixture of space and time. The key insight came from thinking carefully about light. Light travels at a fixed speed about 300,000 kilometers per second in a vacuum, and remarkably, this speed is the same for all observers, regardless of how they're moving. If you're standing still and measure the speed of a passing light beam, you get 300,000 kilometers per second. If you're in a spaceship traveling at half the speed of light and measure a light beam passing you, you still get 300,000 kilometers per second. This constancy seemed impossible under Newton's framework. If you're moving toward a light source, shouldn't the light reach you faster? And if you're moving away, shouldn't it reach you slower? But experiments showed otherwise. Light's speed was stubbornly constant. Something had to give. Einstein realized that space and time themselves must be flexible. What remains constant is the speed of light. What changes is how observers measure distances and durations. If you move relative to me, your meter sticks shrink, length contraction, and your clocks slow down, time dilation. These aren't illusions or measurement errors. They're real physical effects arising from the structure of spacetime. This means time is not the same for everyone. If you travel at high speed relative to Earth, your clock ticks more slowly than clocks on the ground. When you return, less time has passed for you than for those who stayed behind. This isn't science fiction. It's been measured with atomic clocks on airplanes, with GPS satellites, with particles in accelerators. The effect is tiny at everyday speeds, but it grows dramatic as you approach light speed. At 90% of light speed, your clock runs at about 44% the rate of a stationary clock. At 99.9% of light speed, it runs at about 4.5% the rate. Travel for what feels like a year at that speed, and more than 22 years will have passed for those at rest. This time dilation shows that time is not absolute, it's relative dependent on motion. And because it's intertwined with space, we need to think of them together. Space-time. Mathematically, space-time is described as a four-dimensional continuum. Every event, everything that happens can be labelled with 4 coordinates. 3 for where it occurred in space, 1 for when it occurred in time. An event is a point in space-time, much like a location is a point in space. But there's an important difference between the space dimensions and the time dimension. You can move freely in space, walk north or south, east or west, up or down, but you can't move freely in time. You're dragged through time at a rate of 1 second per second, always forward, never backward. This asymmetry shows up in the mathematics. The space-time metric, the mathematical object that describes distances in space-time, treats time with a different sign than space. Space dimensions contribute positively to distances. Time contributes negatively, or vice versa, depending on convention. This difference in sign reflects the deep distinction between space and time, even as they're unified into space-time. The arrow of time, the fact that time flows in one direction, is one of the deepest mysteries in physics. It seems to be connected to entropy, the tendency of systems to move from order to disorder. In a closed system, entropy always increases. Eggs break but don't spontaneously reassemble. Heat flows from hot to cold, not the reverse. This directionality gives time its arrow. Why entropy increases is tied to statistics and the initial conditions of the universe. There are vastly more ways for a system to be disordered than ordered, so disorder is overwhelmingly more likely. And the universe began in an extraordinarily low entropy state, the Big Bang, so it's been increasing in entropy ever since, giving time its forward direction. Einstein's 1915 general theory of relativity extended the unification of space and time even further. General relativity describes gravity not as a force pulling objects together, but as the curvature of space-time itself. Mass and energy warp space-time, creating creating curves and dimples. Objects moving through this curved spacetime follow paths that look to us like gravitational attraction. Earth orbits the Sun not because the Sun exerts a pulling force across empty space, but because the Sun's mass curves spacetime, and Earth follows the straightest possible path through that curved geometry, a geodesic. This makes spacetime dynamical. It's not a fixed background, but an active participant in physics. Matter tells spacetime how to curve, and spacetime tells matter how to move. Time itself can be affected by gravity. Clocks run slower in strong gravitational fields, a phenomenon called gravitational time dilation. A clock on the surface of Earth runs slightly slower than a clock on a mountaintop, because Earth's gravitational field is stronger at the surface. The effect is minuscule, but it's real and measurable. GPS satellites must account for it. Without corrections for both the speed of the satellites and their position in a weaker gravitational field, GPS navigation would drift off course by kilometers within a day. Near massive objects, time dilation becomes extreme. Near a black hole's event horizon, time slows to a crawl relative to distant observers. If you could hover just outside a black hole and wave to a friend far away, your friend would see you moving in extreme slow motion, your waves taking hours or days. Meanwhile, from your perspective, the universe outside would appear to speed up dramatically. This intertwining of space and time, this flexibility of both, is why physicists speak of time as a fourth dimension. Not because it's identical to the three spatial dimensions, clearly it's different, but because it's part of the same geometric structure. To describe reality fully, you need 4 coordinates, 3 of space, 1 of time. The discovery that time is a dimension reshaped all of physics. It changed how we think about causality, simultaneity, and the nature of reality itself. Events that seem simultaneous to one observer might not be simultaneous to another. The question, is event A happening now, doesn't have a universal answer. It depends on your frame of reference. This relativity of simultaneity is deeply counterintuitive. We feel like the present moment is shared by everyone, that there's a universal now spreading across the cosmos. But relativity says there isn't. The present is relative. Different observers slice space-time into space and time differently, like cutting a loaf of bread at different angles. And yet, despite these strange features, space-time is not arbitrary or chaotic. It has structure. There are invariant quantities that all observers agree on. The space-time interval between 2 events, a combination of space and time separations, is the same for all observers, even though they might disagree about the space separation and time separation individually. This structure allows physics to make predictions. It allows us to calculate how particles move, how light bends, how black holes form. The 4-dimensional geometry of space-time becomes a tool for understanding the universe, but as successful as 4-dimensional space-time has been, it's not the end of the story. Because when physicists tried to extend these ideas, when they tried to incorporate quantum mechanics or unify all the forces, 4 dimensions began to feel constraining. The equations demanded more room, and that demand is what led to the next discovery that perhaps dimensions don't stop at 4. Time as a dimension also changes how we think about existence itself. In classical physics, the universe was a 3-dimensional space evolving through time. At each moment, there was a now, a 3-dimensional snapshot of all that existed. The past was gone, the future not yet real. But in space-time, past, present and future all exist together. They're different slices of the 4-dimensional whole. Your birth, your present moment, and your future are all points in space-time, all equally real in some sense. This block universe view troubles some philosophers because it seems to eliminate free will and the flow of time. But it's a natural consequence of relativity. If simultaneity is relative, if different observers disagree about which events are happening now, then there can't be a universal present moment. Instead, all of space-time is simply there, a 4-dimensional structure that we move through, experiencing it one moment at a time, but not creating it as we go. Whether this view is correct philosophically remains debated, but physically, treating time as a dimension has proven extraordinarily successful. It's the foundation of modern cosmology, particle physics and our understanding of black holes and the Big Bang. Once Einstein revealed that spacetime could curve, physics was never the same. The idea that gravity is geometry, that massive objects warp the fabric of spacetime itself, transformed our understanding of the universe. But it also raised new questions. What shape is spacetime? Is it flat, curved, or something more complex? And could this curvature be a clue to hidden dimensions? In special relativity, spacetime is flat. It stretches uniformly in all directions, with no warps or bends. Objects moving through it follow straight lines unless acted upon by forces. But special relativity only applies when gravity is weak or absent. General relativity introduces curvature. Mass and energy don't just exist in space-time, they shape it. Imagine a trampoline with a bowling ball placed in the centre. The fabric sags, creating a depression. Roll a marble nearby, and it curves toward the bowling ball, not because of a force pulling it, but because the surface itself is curved. Space-time works similarly, but in 4 dimensions rather than 2. The Sun curves space-time around it, and Earth follows a curved path through this geometry, an orbit that looks like attraction but is really just motion through curved space. This curvature isn't just a local effect. The entire universe has a shape determined by its total mass and energy content. Cosmologists describe 3 possibilities: flat, positively curved, like the surface of a sphere, or negatively curved, like a saddle. In a flat universe, parallel lines never meet, and the angles of a triangle add up to 180 degrees, ordinary Euclidean geometry. Current measurements suggest our universe is very close to flat, though tiny deviations are possible. In a positively curved universe, space curves back on itself, like the surface of a sphere. Travel far enough in one direction, and you'd eventually return to your starting point. Parallel lines converge, and triangles have more than 180 degrees. Such a universe would be finite but unbounded, no edges, but limited in extent. In a negatively curved universe, space curves outward like a saddle. Parallel lines diverge, triangles have less than 180 degrees, and the universe extends infinitely, but with an unusual geometry. Which type of universe we live in affects its ultimate fate. A positively curved universe dominated by matter would eventually stop expanding and collapse back in on itself a big crunch. A flat or negatively curved universe could expand forever, growing colder and emptier as galaxies drift apart. Current observations from the cosmic microwave background radiation and the distribution of galaxies suggest our universe is flat or very close to it. But flat doesn't mean simple. Even a flat space-time can have complex structures, black holes, gravitational waves, regions of extreme curvature. Black holes are the most dramatic examples of curved space-time. At their centres, according to general relativity, space-time curves infinitely a singularity where the theory breaks down. Around them lies the event horizon, a boundary where the curvature becomes so extreme that not even light can escape. Near a black hole, space-time is so warped that time itself behaves strangely. Clocks slow to a crawl, distances stretch. If you fell toward a black hole, tidal forces differences in gravitational pull between your head and feet would stretch you like spaghetti. From outside, watching someone fall toward a black hole, you'd never see them cross the event horizon. Time dilation would slow their descent asymptotically. They'd appear to freeze at the boundary, forever approaching but never quite reaching it. From their perspective, they'd cross in finite time and experience no barrier, just an irreversible plunge toward the singularity. Gravitational waves are ripples in space-time curvature, spreading outward from violent events like black hole mergers or supernova explosions. Predicted by Einstein but not detected until 2015, these waves stretch and compress space itself as they pass, though by incredibly tiny amounts. The first detected wave, from 2 black holes colliding 1.3 billion light-years away, stretched space on Earth by less than the width of a proton. Detecting gravitational waves opened a new window onto the universe. For the first time, We could observe events through spacetime's vibrations rather than light, and these waves carry information about the nature of spacetime itself, its dimensionality, its structure, its behavior in extreme conditions. The curvature of spacetime also affects light. When light passes near a massive object, its path bends not because the object pulls on it, but because spacetime is curved. This gravitational lensing was one of the first confirmations of general relativity. During a solar eclipse in 1919, astronomers observed stars appearing slightly displaced from their usual positions because the sun's curved spacetime bent their light. Gravitational lensing is now used as a tool. Massive galaxy clusters act as cosmic magnifying glasses, bending light from more distant galaxies behind them. Sometimes this creates multiple images or arcs of the same distant galaxy. By studying these distortions, astronomers can map the distribution of both visible and dark matter. Dark matter, which doesn't emit light, reveals itself through its gravitational effects, the way it curves spacetime. Observations show that galaxies rotate too fast to be held together by visible matter alone. Clusters of galaxies contain far more mass than we can see. The universe's large-scale structure suggests vast amounts of invisible matter, shaping spacetime's geometry. This dark matter makes up about 85% of the universe's matter. We know it's there because of its gravitational effects, but we don't know what it's made of. Could extra dimensions play a role? Some theories suggest dark matter might be ordinary matter confined to a parallel brane, revealing itself to us only through gravity, which leaks into the extra dimensions we share. The shape of spacetime also connects to the Big Bang. Observations show the universe is expanding, galaxies are moving apart, and the farther away they are, the faster they recede. Trace this expansion backward, and you reach a moment about 13.8 billion years ago when everything was compressed into an infinitesimally small, incredibly hot, dense state. What happened at that moment? General relativity predicts a singularity, a point where curvature becomes infinite and the theory breaks down. But physicists suspect this isn't the full story. At such extreme densities and energies, quantum effects must matter. A complete theory of quantum gravity, one that might involve extra dimensions, is needed to describe what really happened. Inflation, a period of exponentially rapid expansion in the first fraction of a second, smoothed out the universe and set the stage for structure formation. But what drove inflation? Some models invoke extra dimensions. Perhaps inflation occurred when dimensions were still large and uncompactified. Perhaps it was driven by the dynamics of branes moving in higher dimensional space. The curvature of spacetime also affects time itself on cosmic scales. In an expanding universe, there's a natural sense of cosmic time, the universal clock that measures the universe's age. But this is only possible because the universe is roughly the same everywhere at large scales. If spacetime were wildly irregular, with some regions expanding fast and others collapsing, no universal time would exist. Understanding spacetime's curvature is essential for cosmology. 4. Studying black holes for testing general relativity. And every test, every observation, every measurement could potentially reveal hints of extra dimensions. If those dimensions affect how spacetime curves, if they leave fingerprints in gravitational waves or the cosmic microwave background, we might detect them indirectly, even if we can't see them directly. The curvature of spacetime shows us that our four-dimensional reality is dynamic, flexible, shaped by the matter and energy it contains. This flexibility is what makes extra dimensions plausible. If 4 dimensions can curve and warp, perhaps additional dimensions could too, curled up so tightly we've never noticed them, but still affecting physics in subtle ways. The response to Einstein's revelation about curved spacetime was initially skeptical. The idea that space itself could bend seemed absurd. How can emptiness have a shape? But the mathematics was elegant, and the predictions were testable. The 1919 eclipse observation of star positions shifting near the Sun was the first dramatic confirmation. Since then, countless experiments have verified general relativity with extraordinary precision. GPS satellites wouldn't work without corrections for both special and general relativistic effects. Gravitational lensing has been observed thousands of times. Gravitational waves have been detected repeatedly. Every test confirms that spacetime curves. And this success suggests we should take the mathematics seriously, even when it leads to strange places like extra dimensions. If curved four-dimensional spacetime describes reality so well, perhaps higher dimensional curved spaces do too, at scales or in configurations we haven't yet probed. The curvature we know might be only part of a larger geometric story. The shape of spacetime in 4 dimensions is remarkable. Its possible shapes in 10 or 11 dimensions, as string theory and M-theory suggest, might be even more so. Each Calabi-Yau manifold, each compactification, each brane configuration represents a different possible geometry. And that geometry, invisible though it may be, could determine the physical laws we observe. 4 dimensions, 3 of space, 1 of time seem to work perfectly for describing the world around us. Stars orbit, planets spin, atoms bind, light travels. General relativity and quantum mechanics each succeed brilliantly in their domains. So why would physicists think we need more dimensions? The answer lies in a profound contradiction at the heart of modern physics. When you try to apply both general relativity and quantum mechanics to the same system, when you try to describe gravity at quantum scales, the two theories clash. They produce infinities, contradictions, nonsensical results. Something is missing. General relativity describes gravity as smooth, continuous curvature of spacetime. It works beautifully for large objects, planets, stars, galaxies, even black holes. But it treats spacetime as a classical field, ignoring quantum effects. Quantum mechanics describes the microscopic world in terms of probabilities, uncertainties, and discrete energy levels. It works beautifully for particles, atoms, and forces like electromagnetism. But it assumes a fixed spacetime background and doesn't account for gravity. Most of the time, this division of labour works fine. Gravity is so weak at atomic scales that you can ignore it when studying quantum systems. And quantum effects are so tiny at large scales that you can ignore them when studying planets and galaxies. But there are situations where both matter. Inside black holes, where space-time curves infinitely, at the Big Bang, when the entire universe was compressed to quantum scales. In the cores of neutron stars, where matter becomes so dense that quantum pressure fights against gravitational collapse. In these extreme conditions, you need a theory of quantum gravity, a framework that unifies general relativity and quantum mechanics. But creating such a theory has proven extraordinarily difficult. When physicists try to apply the standard techniques of quantum field theory to gravity, they encounter infinities that can't be removed. The math breaks down, the predictions become meaningless. Gravity, it seems, resists quantization. This is where extra dimensions enter the picture. One of the earliest hints came in 1919, when Theodore Kaluza discovered that if you extend general relativity from 4 dimensions to 5, something remarkable happens. The equations of 5-dimensional gravity naturally contain Einstein's 4-dimensional gravity, plus Maxwell's equations for electromagnetism. 2 forces seemingly different emerge from a single, unified geometric framework in 5 dimensions. Gravity and electromagnetism aren't separate phenomena, but different aspects of 5-dimensional geometry. This was astonishing. It suggested that unification, bringing different forces under one umbrella, might be achieved by adding dimensions. But there was an obvious problem. We don't see a 5th dimension. Where is it? In 1926, Oscar Klein proposed an answer: compactification. The 5th dimension exists but is curled up into a tiny circle at every point in space, so small, about 10, -35 meters, that we can't detect it directly. From our perspective, the universe looks 4-dimensional. But at every point, there's a hidden circular dimension wrapped up tightly. This Kaluza-Klein theory was the first serious proposal for extra dimensions. It didn't survive as a complete theory. It couldn't explain the strong and weak nuclear forces, which weren't discovered until later. but it established a template, extra dimensions as tools for unification. As physics advanced, the challenge grew more complex. By the mid-20th century, 4 fundamental forces were known: gravity, electromagnetism, the strong nuclear force, binding protons and neutrons, and the weak nuclear force governing radioactive. The electromagnetic and weak forces were successfully unified in the 1,970 seconds into the electro-weak interaction. At high energies, they merge into a single force. The strong force fits into the same mathematical framework, the standard model of particle physics. But gravity remains separate. It won't merge with the others. The standard model describes 3 of the 4 forces beautifully using quantum field theory, but it doesn't include gravity. And when you try to add gravity, the theory breaks. This failure suggests something fundamental is missing, and one possibility is that we're working in the wrong number of dimensions. Perhaps unification requires more room, more degrees of freedom than 4 dimensions provide. String theory emerged in the 1,980 seconds as a potential solution. Instead of treating particles as point-like objects, string theory describes them as tiny vibrating strings. Different vibrational modes correspond to different particles: electrons, quarks, photons, even gravitons, hypothetical quantum particles of gravity. The brilliance of string theory is that it naturally includes gravity. One vibrational mode of a string automatically corresponds to the graviton. Gravity isn't added by hand, it falls out of the mathematics. For the first time, physicists had a framework that could potentially describe all 4 forces, including gravity, within a single quantum theory. But the theory comes with a requirement. It only works in 10 dimensions. Not 4, not 6, 10 9 of space and 1 of time. Try to formulate string theory in fewer dimensions, and mathematical inconsistencies arise. Anomalies appear. The equations don't balance. Why 10? The technical answer involves the structure of the vibrating strings and the need for certain symmetries to cancel out quantum anomalies. But the simple answer is, the math demands it. Later, when different versions of string theory were unified into M theory, the number increased to 11 dimensions. And these aren't just mathematical curiosities. The extra dimensions play essential roles in the theory's structure. They provide the space strings need to vibrate in ways that produce all the particles and forces we observe. This is the contradiction that drives the search for extra dimensions. 4 dimensions aren't enough to describe everything. They're enough for everyday experience, enough for Newton's laws and Einstein's relativity in their respective domains. But they're not enough to unify gravity with quantum mechanics. They're not enough to explain the hierarchy of forces, why gravity is so much weaker than the others. They're not enough to account for certain features of particle physics. The contradiction manifests in specific ways. Gravity's weakness is 1. The electromagnetic force between 2 protons is 10, 36 times stronger than their gravitational attraction. Why such an enormous difference? One explanation: gravity isn't inherently weak, it's diluted, because it spreads into extra dimensions while the other forces stay confined to our 4-dimensional spacetime. Gravity leaks into the bulk of higher dimensional space, making it appear feeble in our slice of reality. Another mystery: dark matter. Observations show that galaxies contain far more mass than we can see. This dark matter doesn't emit or absorb light, but its gravitational effects are unmistakable. Could dark matter particles be Kaluza-Klein excitations, heavier versions of ordinary particles arising from motion in compactified dimensions? Or consider the cosmological constant problem. Quantum field theory predicts a vacuum energy density that's 10, 120 times larger than what we observe. This is the worst prediction in the history of physics. Could extra dimensions help explain why the observed value is so small? These contradictions and mysteries don't prove extra dimensions exist, but they show that 4-dimensional physics leaves fundamental questions unanswered. Extra dimensions offer potential solutions, which is why physicists take them seriously despite their strangeness. The need for more dimensions arises not from desire to complicate things, but but from following the mathematics wherever it leads. If the equations unify forces in 10 dimensions but not in 4, if string theory solves the quantization of gravity but requires extra dimensions, then we have to consider the possibility that those dimensions are real. This is how science often progresses. Theory predicts something unexpected. Skepticism is natural, but if the predictions are precise and potentially testable, the ideas warrant serious attention. Extra dimensions are in this category weird, yes, but grounded in mathematical necessity. The contradiction also appears in attempts to understand the Big Bang. Standard four-dimensional cosmology predicts a singularity, a point where density and curvature become infinite. But infinities in physics usually signal that a theory has reached its limits. Perhaps 4 dimensions are insufficient to describe what happened at the universe's beginning. Higher dimensional physics might smooth out the singularity, replacing it with a more complex but finite process. Some brain cosmology models suggest the Big Bang was a collision between higher dimensional membranes, releasing energy that became our universe. In these scenarios, the extreme conditions of the early universe naturally involve extra dimensions. As the universe cooled and expanded, most dimensions compactified, leaving the 3 large spatial dimensions we experience today. This would mean our 4-dimensional reality is a low-energy approximation. At high energies, like those in the early universe or inside black holes, the full higher dimensional nature of spacetime becomes important. We live in the aftermath of dimensional reduction, in a universe that's settled into 4 dimensions but retains hints of its more complex origins. In 1919, just 4 years after Einstein published his general theory of relativity, a German mathematician named Theodor Kaluza sent Einstein a paper that proposed something audacious. What if Einstein's equations, which described gravity in 4 dimensions, were extended to 5? Kaluza didn't add a 5th dimension arbitrarily. He did it systematically, following the mathematical structure of general relativity and seeing what emerged. And what emerged was startling. The 5-dimensional equations naturally contained not only Einstein's 4-dimensional gravity, but also Maxwell's equations, the complete description of electromagnetism. This was revolutionary. 2 of the fundamental forces of nature, gravity and electromagnetism, which seemed entirely different, could be unified in a 5-dimensional geometric framework. Electromagnetism wasn't a separate force, but an aspect of 5-dimensional gravity. The electric and magnetic fields were components of the 5-dimensional gravitational field, revealed when you project down to 4 dimensions. Think about what this means. In 3 dimensions, a sphere's shadow on a wall looks like a circle. The circle is real, you can see it, but it's just a projection of the higher dimensional object. Similarly, electromagnetism might be a 4-dimensional shadow of 5-dimensional gravity. Einstein was intrigued but cautious. The mathematics was elegant, but the physical interpretation was unclear. If there's a 5th dimension, why don't we see it? Why does space appear 3-dimensional? In 1926, Swedish physicist Oskar Klein proposed an answer. Compactification. The 5th dimension exists but is curled up into a tiny circle at every point in space. Imagine an ant crawling on a very thin tube. From far away, the tube looks 1-dimensional, just a line. But the ant perceives a 2nd dimension, the circular cross-section of the tube. The circle is real, but it's so small relative to the tube's length that it's invisible from a distance. Klein suggested the 5th dimension works the same way. At every point in our familiar 3-dimensional space, there's a tiny circular dimension, curled with a radius on the order of the Planck length, about 10, -35 meters. Far too small for any experiment to detect. This compactification solves the "where is it?" problem. The 5th dimension is everywhere, at every point, but it's hidden by its tiny size. You can't move into it in any noticeable way, because moving a full circle's worth would be an incredibly tiny displacement, trillions of times smaller than an atom. The Kaluza-Klein theory was mathematically beautiful and conceptually bold. It showed that unification might be achieved not through new forces but through new dimensions. Geometry, not particles or fields, could be the underlying reality. But the theory had limitations. It only unified two forces, gravity and electromagnetism. The strong and weak nuclear forces, discovered later, weren't explained. And the theory made predictions that didn't match observations. For instance, it predicted new particles' Kaluza-Klein modes arising from motion in the fifth dimension. These should show up as heavier versions of known particles. None were found. Moreover, stabilizing the compactified dimension was difficult. Why would it curl up to a specific size and stay there? What prevents it from expanding or collapsing? The theory lacked a mechanism. Despite these problems, Kaluza-Klein theory established crucial concepts that would resurface decades later in string theory. The idea that extra dimensions could be real but hidden through compactification. The notion that forces might be geometric effects in higher dimensions. The possibility that particle properties, masses, charges could depend on the geometry of hidden spaces. Mathematically, here's what happens. When you write Einstein's equations in 5 dimensions, you get more components than in 4 dimensions. Some components describe how the familiar 4-dimensional spacetime curves that's gravity as we know it. But there are additional components associated with the 5th dimension. These extra components turn out to satisfy Maxwell's equations. The electric field, the magnetic field, and the electromagnetic potential all emerge naturally from the geometry of the 5th dimension. This wasn't a coincidence or trick. It was a deep connection between geometry and physics. It suggested that what we perceive as forces, electromagnetic attraction and repulsion might really be manifestations of curved higher dimensional space, just as gravity is curves in 4-dimensional spacetime. Electromagnetism could be curves in 5-dimensional spacetime. Klein's compactification introduced another crucial idea. The size of the extra dimension matters. If it's too large, we'd notice it. Objects would have momentum in that direction, and we'd observe extra degrees of freedom. If it's too small, quantum effects would make it unobservable. Klein estimated that for the theory to match observations, the 5th dimension's radius should be about 10 - 30 centimeters later, refined to the Planck length, 10 - 33 centimeters. At such scales, particles moving in the compact dimension would have quantized momentum, just like electrons in atoms have quantized energy levels. These quantized states appear in 4 dimensions as particles with different masses, the Kaluza-Klein tower of particles. The lightest state corresponds to particles at rest in the 5th dimension, ordinary particles. Excited states correspond to particles moving in the 5th dimension, heavier versions of ordinary particles. This prediction is testable in principle. If we could reach high enough energies in particle colliders, we might create these Kaluza-Klein excitations, revealing the 5th dimension indirectly through its particle spectrum. So far, none have been detected. Which means either the 5th dimension doesn't exist, or it's even smaller than initially thought, requiring higher energies to probe. The Kaluza-Klein theory faded from prominence for decades. Without experimental evidence and without explaining the strong and weak forces, it seemed like an interesting but incomplete idea. But it never quite died. Physicists remembered it as an example of how extra dimensions might work. When string theory emerged in the 1980 seconds, Kaluza-Klein's legacy was central. String theory required extra dimensions, not just 1, but 6 beyond the usual 4. And the compactification of those dimensions worked exactly as Klein had proposed, curling them up into tiny shapes invisible at accessible scales. The geometry of the compactified dimensions became crucial. In Kaluza-Klein theory, with 1 extra dimension, the circle's radius was the only parameter. In string theory, with 6 extra dimensions, the geometry is vastly more complex. The shapes are called Calabi-Yau, manifolds intricate 6-dimensional spaces with special symmetry properties. Different Calabi-Yau manifolds lead to different physics in 4 dimensions. The shape determines which particles exist, their masses, how forces behave. In this picture, the laws of physics aren't arbitrary. They're determined by higher dimensional geometry. This makes the question, what shape are the extra dimensions? Fundamental. It's not just an abstract mathematical question, it determines reality as we experience it. Our universe's specific properties might be the result of the particular Calabi-Yau manifold that nature chose, or that arose dynamically when the extra dimensions compactified. Kaluza and Klein couldn't have imagined how influential their idea would become. They were working before quantum mechanics was fully developed, before the strong and weak forces were discovered, before particle physics revolutionized our understanding of matter. But they glimpsed a deep truth. That dimensions might be tools for unification, that geometry might underlie forces, and that reality could be richer than appearances suggest. Their bold step adding one dimension and following the mathematics set a pattern that continues today. When equations demand more dimensions, physicists take the demand seriously. When geometry offers explanations, we explore where it leads. And when reality seems to hide aspects of itself, we ask how they might be tucked away, too small or too subtle for direct observation but still influencing what we can measure. The Kaluza-Klein framework also introduced the crucial distinction between large and small dimensions. Not all dimensions need to be equal. Some can extend infinitely, or cosmologically, while others curl up at microscopic scales. This asymmetry seems strange until you realize that explaining it might itself be a clue about physics. Why did three spatial dimensions stay large while others, if they exist, compactified? Perhaps it's related to the dynamics of the early universe. Perhaps certain dimensions were stabilized by fields or forces we don't yet understand. Perhaps it's anthropic only in universes where three dimensions expand can complex structures like stars and life arise. This selection effect would explain why we observe three large dimensions. We couldn't exist in a universe configured differently. Whether or not you find anthropic reasoning satisfying, the question remains deep. What mechanism selects which dimensions expand and which curl up? Kaluza and Klein opened this question without answering it. String theory and M-theory inherited the puzzle, and it remains one of the central mysteries of higher dimensional physics. By the 1980 seconds, physics was in a peculiar state. The standard model of particle physics worked brilliantly, describing three of the four fundamental forces with extraordinary precision. But gravity remained outside the framework, stubbornly resisting all attempts at quantization. General relativity was equally successful in its domain describing cosmic structures, black holes, gravitational waves. But the two great theories couldn't be reconciled. Whenever physicists tried to apply quantum field theory to gravity, the mathematics exploded into infinities that couldn't be tamed. The techniques that worked for electromagnetism, the strong force and the weak force, failed utterly when applied to spacetime curvature. This is where string theory entered as a potential solution, and almost immediately it made an extraordinary demand. 10 dimensions, not 4, not 5, but 10 9 of space and 1 of time. The central idea of string theory is deceptively simple. Instead of treating fundamental particles as point-like objects with no internal structure, imagine them as tiny, one-dimensional strings. These strings can be open with two endpoints or closed forming loops, and they vibrate. Just as a guitar string can vibrate at different frequencies to produce different musical notes, these fundamental strings can vibrate in different modes. Each vibrational pattern corresponds to a different particle. One mode produces what we observe as an electron, another produces a quark, another produces a photon, another crucially produces a graviton, the hypothetical quantum particle of gravity. This is revolutionary. In string theory, particles aren't fundamental. Strings are. What we call different particles are just different vibrations of the same underlying string. It's an elegant unification. One object, many manifestations, and gravity emerges automatically. One of the vibrational modes of a closed string behaves exactly like a graviton, a massless spin two-particle that mediates gravitational interactions. You don't add gravity to string theory. It's already there, woven into the fabric of how strings vibrate. For the first time, physicists had a quantum theory that included gravity, not as an afterthought but as a natural, unavoidable consequence. This was thrilling. But it came with a price. The theory only worked consistently in 10 dimensions. Why 10? The technical explanation involves mathematical consistency requirements called anomaly cancellation. In quantum field theories, certain symmetries can be violated by quantum effects. These violations are anomalies. If anomalies aren't cancelled, the theory makes nonsensical predictions, probabilities that don't add up to 1, conservation laws that are violated, causality that breaks down. For string theory to be free of anomalies, the strings need to vibrate in a space with exactly 10 dimensions, 9 spatial, 1 temporal. In fewer dimensions, anomalies appear that can't be removed. In more than 10, other problems arise. 10 is the sweet spot where everything works. This wasn't arbitrary. The requirement emerged from the mathematics organically. When physicists calculated how strings behave quantum mechanically, 10 dimensions fell out as necessary. It was like asking, what shapes can tile a plane? And discovering that only certain regular polygons work. Nature seems to have structural requirements, and for strings, 10 dimensions is one of them. But we don't experience 10 dimensions, we experience 4. So the obvious question returned, where are the other 6? The answer, borrowed from Kaluza and Klein, is compactification. The 6 extra spatial dimensions are curled up into a tiny shape at every point in space. So small on the order of 10, negative 35 meters, the Planck length that they're invisible to current experiments. But unlike Kaluza-Klein theory, which compactified 1 dimension into a circle, string theory compactifies 6 dimensions into much more complex shapes. The geometry can't be arbitrary. The compactified space must have special properties to preserve the symmetries that make string theory work. The shapes that satisfy these requirements are called Calabi-Yau manifolds, named after mathematicians Eugenio Calabi and Xingtung Yau. These are intricate 6-dimensional geometries with beautiful mathematical properties, but almost impossible to visualize. Imagine trying to picture a 6-dimensional object. Even a 4-dimensional hypercube strains intuition. Calabi-Yau manifolds are far more complex folded, curved spaces with holes, tunnels, and topological features that have no analogue in our 3-dimensional experience. Yet these shapes are crucial. The specific Calabi-Yau manifold, chosen or arising dynamically, determines the physics we observe in 4 dimensions. Different shapes produce different particle spectra, different force strengths, different physical laws. This is both beautiful and problematic. Beautiful because it suggests the laws of physics aren't arbitrary, but derive from geometry. Problematic because there are many possible Calabi-Yau manifolds, estimates suggest around 500 different shapes that could work. With so many possibilities, how do we know which one describes our universe? This vast number of solutions is called the string landscape. Each point in the landscape represents a different compactification, a different possible universe with different physical laws. Our universe would be just one point among countless others. Some physicists find this landscape troubling. If string theory allows 500 different universes, is it really predictive? Or does it just accommodate any observation by selecting the appropriate vacuum? Others see the landscape as a feature, not a bug. Perhaps all these possibilities are realized in a vast multiverse, and we observe this particular set of laws because we happen to live in this particular compactification. The requirement of 10 dimensions also changes how we think about particles. In string theory, particle masses, charges, and interaction strengths all depend on the compactified geometry. The shape of the hidden dimensions determines which particles exist and how they behave. For instance, electrons have negative charge and a specific mass. In string theory, these properties aren't fundamental but arise from how strings wrap around and vibrate in the Calabi-Yau space. Change the geometry, and you change the particle properties. This means the question, why does an electron have this mass? Transforms into, why does the compactified space have this shape? It shifts the mystery from particle physics to geometry, which may or may not be progress depending on your perspective. String theory also predicts new particles beyond those in the standard model. Just as Kaluza-Klein theory predicted massive versions of ordinary particles from momentum in the extra dimension, string theory predicts superpartners' heavier versions of known particles arising from supersymmetry, a symmetry relating bosons, force carriers, and fermions, matter particles. None of these superpartners have been found yet. The Large Hadron Collider has searched extensively, reaching energies where some superpartners were expected to appear. Their absence pushes the predicted masses higher, suggesting either that supersymmetry is broken at higher scales than hoped, or that string theory's predictions need refinement, or possibly that the theory is wrong, but absence of evidence isn't evidence of absence, especially when you're probing scales far below the Planck length where string theory's effects should be strongest. Current colliders reach energies around 10, 4 GeV, giga electron volts. The Planck energy, where strings themselves become important, is about 10, 19 GeV, 15 orders of magnitude higher. We're not even close. This is string theory's biggest challenge: testability. The theory makes precise mathematical predictions about physics at the Planck scale, but that scale is unreachable with any conceivable experiment. The compactified dimensions are too small to see directly, the energies are too high to probe, so instead, physicists look for indirect signatures. Does string theory explain certain puzzles in the standard model? Can it account for dark matter or a dark energy? Does it make testable predictions about cosmology, the early universe, or black holes? Some progress has been made. String theory provides a framework for calculating black hole entropy, matching predictions from thermodynamics. It offers mechanisms for inflation and explanations for certain features of the cosmic microwave background. It connects to observable physics through dualities, mathematical equivalences that link string theory to more accessible quantum field theories. The ADS CFT correspondence, discovered in 1997, is the most famous example. It shows that a string theory in a particular type of five-dimensional curved space, anti-de Sitter space, is exactly equivalent to a quantum field theory without gravity in four-dimensional flat space. This duality allows physicists to calculate things in one theory by using the other, providing tools for studying strongly interacting systems in particle physics and even condensed matter. But none of this is direct evidence that strings exist or that the universe has 10 dimensions. It's circumstantial, supportive, but not definitive. Still, the requirement of 10 dimensions isn't arbitrary. It emerges from consistent quantum behavior. It's a structural necessity for the theory to work, and the fact that gravity appears automatically, that forces unify naturally, that quantum mechanics and general relativity coexist peacefully, all of this suggests string theory captures something true about reality, even if we don't yet know how to test it directly. The investigation continues. Physicists refine the theory, exploring its mathematical structure, looking for corners where predictions touch observable physics. They study how strings behave near black holes, how they produce inflation, how they might explain the accelerating expansion of the universe. And they grapple with the central question: are the 10 dimensions of string theory real, or are they just mathematical scaffolding useful for calculations but not physical? The answer isn't yet clear, but the requirement itself that strings need 10 dimensions to vibrate consistently remains one of the most striking facts in theoretical physics. The 10 dimensions of string theory also reshape how we think about unification. In 4 dimensions, the fundamental forces seem distinct. Gravity acts on mass, electromagnetism on charge, the strong force on color charge, the weak force on certain particle types. But in 10 dimensions, these distinctions might blur. All forces could be aspects of 10-dimensional geometry, just as Kaluza showed that 5-dimensional geometry contains both gravity and electromagnetism. String theory suggests that at high enough energies near the Planck scale, all forces merge into a single unified interaction. The splitting we observe at low energies is an artifact of compactification and symmetry breaking. This unification is elegant, but it happens at energies we can't reach, in dimensions which we can't see. We're left inferring the structure from shadows and echoes, from mathematical consistency and indirect effects. The 10 dimensions remain hidden, essential to the theory but elusive in practice. In the early 1990 seconds, string theory faced an embarrassing problem. Instead of one unified theory, there were 5 different versions. Each was mathematically consistent. Each required 10 dimensions. Each described vibrating strings and included gravity. But they had different structures, different types of strings, different symmetries. This was awkward. If string theory was supposed to be the final, unified theory of everything, why did it come in 5 flavors? It was like discovering that the ultimate truth had 5 different, apparently contradictory formulations. Physicists knew these theories must be related somehow. They shared too many features to be completely independent. But the connections weren't obvious. The 5 theories seemed to describe different worlds, different physics. Then in 1995, Edward Witten proposed something radical. The 5 string theories weren't separate theories at all. They were different perspectives on a single, deeper theory. And that deeper theory, eventually called M-theory, required not 10 dimensions, but 11. This was the data that changed everything. M-theory unified the string theories by embedding them in an 11-dimensional framework. The 5 versions were like different slices through a larger structure, different limits of a more fundamental reality. The 11th dimension did more than just unify. It introduced new objects into the theory. String theory focused on one-dimensional strings, but in 11 dimensions, 2-dimensional membranes called two-branes or just membranes appear naturally. So do higher dimensional objects, 3 branes, 4 branes, all the way up to 9 branes in 10-dimensional versions. Our entire observable universe might be a 3-brane, a 3-dimensional membrane floating in the 11-dimensional bulk. Everything we know, all matter, all forces except gravity, could be confined to this brane. We can't leave it or see beyond it. We're like drawings on a sheet of paper, perceiving only the surface we inhabit. Gravity, in contrast, isn't confined. It permeates all 11 dimensions. This offers a natural explanation for why gravity is so weak. Its influence is diluted across the extra dimensions, while the other forces stay concentrated on our brain. The 11th dimension is sometimes described as being different from the others, extended rather than compactified in some scenarios, or playing a special role in the structure of the theory. But its presence is mathematically necessary. Just as string theory demands 10 dimensions, M-theory demands 11. Why 11 specifically? 11 turns out to be the maximum number of dimensions in which supergravity, a theory combining supersymmetry and general relativity, can exist consistently. Beyond 11, the equations break down. 11 is a natural endpoint, a boundary in the space of possible theories. The M in M-theory has never been officially defined. Different physicists interpret it differently. Membrane, since brains are central to the theory. Mother, since it encompasses the 5 string theories. Mystery, since much about it remains unknown. Magic, for its mathematical beauty. Or simply M, waiting for future understanding to reveal what it truly stands for. Unlike string theory, which has well-developed mathematical formalism, M-theory exists more as a framework, a collection of relationships, dualities, and principles that connect the string theories, but without a complete set of defining equations. Physicists know it requires 11 dimensions, includes branes, unifies the string theories, and reduces to specific string theories in certain limits. But the full theory remains unfinished. This incompleteness might seem like a weakness, but it's also honest. Physics is a work in progress. M-theory represents the best current understanding of how string theories fit together, even if all the pieces haven't been assembled yet. The data from M-theory reshaped thinking about cosmology. If our universe is a 3-brane, perhaps the Big Bang was a collision between branes in higher dimensional space. 2 branes drifting through the bulk crash together, releasing enormous energy that becomes the hot, dense state we call the Big Bang. This ekpyrotic scenario, from the Greek word for conflagration, offers an alternative to traditional inflation. Instead of a scalar field driving rapid expansion, Brane collisions provide the energy. The universe doesn't begin from a singularity, but from a collision event in higher dimensions. Such collisions could be cyclic. Branes might collide, rebound, drift apart, and collide again, creating a series of universes. Each cycle produces a big bang, an expanding universe, eventual contraction, and another collision. Time extends infinitely in both directions, with our universe just one cycle among many. These scenarios are speculative but testable in principle. Brane collisions would leave specific signatures in the cosmic microwave background patterns of temperature fluctuations that differ from standard inflation. Observations haven't found such signatures yet, but searches continue. M-theory's 11 dimensions also affect how we think about black holes. In higher dimensions, black holes can have different properties. They can be string-like, black strings, or membrane-like black branes, extended objects rather than points. These exotic black holes might exist in the bulk, influencing our brain through their gravitational effects. Studies of black hole entropy in M-theory have been remarkably successful. By counting the quantum states of branes wrapping around compactified dimensions, physicists can reproduce the entropy predicted by classical general relativity. This is one of M-theory's concrete achievements, a quantum derivation of a macroscopic result. The relationship between M-theory and string theory is subtle. M-theory isn't replacing string theory but completing it. The 5 string theories are approximations valid in certain limits, where one dimension is much smaller than the others, or where certain parameters take specific values. M-theory is the complete picture that encompasses all these limits. Think of it like a map projection. The surface of a sphere, Earth, can be represented by different flat maps, Mercator, Robinson, azimuthal. Each distorts the globe differently, but captures some features well. No single map is perfect, but they're all representations of the same sphere. Similarly, the 5 string theories are different projections of M-theory, each useful in certain contexts. The dualities connecting the theories are particularly striking. 2 seemingly different theories can describe exactly the same physics. Strong coupling in one theory corresponds to weak coupling in another. Large distances in one theory correspond to short distances in another. These dualities reveal hidden symmetries and suggest that our distinctions between theories might be artifacts of perspective. One famous duality, called T-duality, relates small and large compactified dimensions. If a dimension is curled into a circle of radius r in one theory, there's a dual theory where the same dimension has radius 1, r. String winding around the small circle in the first theory corresponds to string momentum in the large circle of the dual theory. The physics is identical, just described differently. This suggests that below a certain scale around the Planck length, the concept of distance loses meaning. You can't distinguish between a very small dimension and a very large one. They're physically equivalent, related by duality. S-duality relates strong and weak coupling. A theory with strong interactions, hard to calculate, is equivalent to a dual theory with weak interactions, easy to calculate. This provides a powerful tool. Calculations impossible in one theory become straightforward in its dual. These dualities aren't just mathematical tricks. They reveal something deep about the structure of reality. They suggest that our description of nature, which dimensions we choose, which variables we use, which theory we apply is conventional. The underlying truth is richer than any single formulation. 11 dimensions in M-theory don't make the picture simpler, but they do make it more complete. They provide room for all the structures, strings, branes, dualities needed to unify gravity with quantum mechanics. They explain why 5 string theories exist. They're different views of the same 11-dimensional reality. The number 11 isn't arbitrary or decorative. It emerges from consistency requirements, from the mathematics of supergravity, from the need to incorporate all the phenomena that 10-dimensional string theories revealed. 11 dimensions are necessary for the theory to hold together. Whether these 11 dimensions are real in a physical sense or useful fictions that organize our calculations remains unclear. No experiment has detected them directly, but their mathematical necessity is undeniable. And in physics, mathematical necessity often points toward physical truth. The data from M-theory also suggests something profound about emergence. Perhaps our four-dimensional spacetime isn't fundamental, but emerges from 11-dimensional dynamics at low energies. Just as temperature emerges from molecular motion, four-dimensional physics might emerge from 11-dimensional geometry. This would mean that the reality we experience, space, time, particles, forces, is all effective, approximate, valid at our scale but not ultimate. The true fundamental description might be 11-dimensional, with our world as a derived consequence. This perspective is both humbling and exciting. Humbling because it suggests we're even farther from fundamental reality than we thought. Exciting because it means there's deeper structure to discover. M-theory, incomplete as it is, offers a glimpse of that structure. 11 dimensions aren't the end of the story. They're a waypoint, a piece of the puzzle, a step toward understanding what the universe really is. The data points to 11, but the meaning of those 11 continues to unfold. If extra dimensions exist, the obvious question is, where are they? Why don't we see them? Why don't we bump into them when we move, or fall into them when we stumble? The answer lies in one of the most elegant and frustrating concepts in theoretical physics: compactification. The extra dimensions aren't missing, they're hidden, curled up so tightly at every point in space that they're invisible to us, too small for our instruments to detect, too tiny for even atoms to explore. Imagine you're an ant on a tightrope stretched across a canyon. From your perspective, there's one dimension to travel, forward or backward along the rope. But if you look closely at the rope, you discover it has thickness. There's a second dimension circular, wrapped around the rope's axis. You can walk along the length, but you can also walk around the circumference. If the rope is very thin, and you're very large relative to it, you might never notice the circular dimension. It would be too small to matter. That's compactification. The dimension exists, but it's curled into a space so small that it's effectively invisible. Oscar Klein first proposed this idea in the 1,920 seconds for a single extra dimension. He imagined it curled into a circle with a radius of about 10, -30 centimeters later, refined to 10, -33 centimeters, the Planck length. At every point in our familiar three-dimensional space, there would be an additional tiny circle. Objects could have momentum in this circular dimension, but we'd perceive it as a property like mass or charge, not as motion through space. String theory extends this concept to 6 extra dimensions, curled not into simple circles but into complex 6-dimensional shapes called Calabi-Yau manifolds. These shapes are far more intricate than circles. They have holes, tunnels, curves, and topological features that exist in 6 dimensions but are impossible to visualize directly. Why these specific shapes? Because string theory requires them. The compactified space must preserve certain symmetries, supersymmetry in particular, for the theory to remain consistent. Only Calabi-Yau manifolds and a few other special geometries meet these requirements. Think of it this way: not every shape can tile a floor without gaps or overlaps. Only certain geometries work: squares, triangles, hexagons. Similarly, not every 6-dimensional shape can host string theory without creating contradictions. Calabi-Yau manifolds are the shapes that work. But there are many Calabi-Yau manifolds, perhaps hundreds of thousands, perhaps millions, perhaps 10, 500 or more, depending on how you count. Each represents a different possible compactification, and each would produce different physics in the observable 4 dimensions. This is both the beauty and the problem of compactification. The beauty is that it connects geometry to physics in a profound way. The shape of the hidden dimensions determines which particles exist, what masses they have, how strongly they interact. In principle, all the parameters of the standard model, the electron's mass, the strength of electromagnetism, the number of particle generations, could be explained by geometry. The problem is that with so many possible shapes, how do we know which one describes our universe? String theory doesn't uniquely predict the compactification. Instead, it allows a vast landscape of possibilities, each corresponding to a different set of physical laws. Some physicists find this troubling. If the theory doesn't predict unique values for particle masses and coupling constants, is it really predictive? Or is it just flexible enough to accommodate any observation by choosing the right compactification? Others argue that the landscape is actually a feature. Perhaps all these compactifications are realized somewhere in a vast multiverse. Different regions of a larger cosmos might have different compact geometries, different physical laws. We observe this particular set of laws because we happen to live in a region with this particular compactification, and perhaps only this compactification allows complex structures like stars and life. This anthropic reasoning is controversial but not absurd. If the universe is much larger than what we can observe, and if different regions have different compactifications, then selection effects become important. We necessarily find ourselves in a region compatible with our existence. The details of compactification matter enormously. Consider the simplest case. Klein's circle. If you move around the circle and return to your starting point, you've travelled a full circumference. Quantum mechanically, this means momentum in that direction is quantized. It comes in discrete units related to the circle's size. These quantized momentum states appear in our four-dimensional world as particles with different masses. The zero momentum state corresponds to ordinary particles. Higher momentum states Kaluza-Klein. Excitations appear as heavier versions of ordinary particles. The smaller the circle, the larger the gaps between these mass levels. If the radius is the Planck length, the lightest Kaluza-Klein excitation would have a mass around the Planck mass about 10, 19 GeV, far beyond what any collider can produce. That's why we haven't seen these particles. They're too heavy to create with available energies. For six-dimensional Calabi-Yau manifolds, the situation is vastly more complex. Instead of a single circular dimension, you have a six-dimensional space with rich topology. Strings can wrap around different cycles in this space, like rubber bands stretched around a complicated surface in different ways. Each wrapping mode corresponds to a different particle. The size and shape of the Calabi-Yau manifold determine particle properties. For instance, the electron's mass might depend on the volume of a particular two-dimensional surface embedded in the six-dimensional space. Change the geometry slightly, and you change the electron's mass. This raises a stability problem. What keeps the compactified dimensions at a particular size and shape? What prevents them from expanding back to macroscopic scales or collapsing to zero size? In string theory, the answer involves fields called moduli. These are fields associated with the size and shape parameters of the compactification. To stabilize the extra dimensions, these moduli must have a potential energy that reaches a minimum at the desired configuration. Finding mechanisms to generate such potentials and fix the moduli has been a major research direction. One successful approach involves fluxes, field configurations, wrapped around cycles in the compact space, like magnetic fields threading through a donut hole. These fluxes generate potentials that can stabilize most, though not all, moduli, locking the compactification into a specific configuration. Compactification also connects to cosmology. In the early universe, when temperatures were extraordinarily high, the extra dimensions might have been as large as the familiar 3. As the universe expanded and cooled, most dimensions compactified while 3 remained large. Why 3? Perhaps it's dynamical. Certain numbers of large dimensions are more stable or more probable in the compactification process. Perhaps it's environmental-only universes, with 3 large spatial dimensions form stable atoms, stars, and observers. Or perhaps there's a deeper principle we haven't discovered yet. Detecting compactified dimensions is extraordinarily difficult but not impossible. One approach looks for missing energy in particle collisions. If particles can escape into extra dimensions, particularly if gravity can, then collisions would show energy imbalance, more energy going in than coming out in observable particles. Another approach examines gravity at short distances. If extra dimensions exist at scales, we can probe much larger than the Planck length in some scenarios. Gravity's strength should deviate from the inverse square law at those distances. Experiments using torsion balances and atom interferometry test this, probing down to sub-millimeter scales. So far, no deviations have been found. Cosmological observations also constrain compactification. The shape and size of extra dimensions would affect the early universe's evolution, potentially leaving signatures in the cosmic microwave background. The pattern of temperature fluctuations could reveal whether extra dimensions were present during inflation. Compactification transforms the question of extra dimensions from "do they exist?" to "how are they hidden?" It provides a mechanism that's consistent with observations, while allowing for the rich higher dimensional structure that string theory and M-theory require. But it also introduces new mysteries. Which shape did nature choose? How did compactification happen? What determines the size? These questions remain at the frontier of theoretical physics, unanswered but actively investigated. The deeper mystery of compactification is why it's stable. In the early universe, all dimensions should have started on equal footing. What selected three to expand while the others curled up? One possibility is that it's not stable at all, that the compactified dimensions are slowly evolving, changing size or shape over cosmic timescales. Such evolution would alter physical constants gradually. We see no evidence for this, but the changes might be too slow to detect over human timescales. Another possibility is that many attempts at compactification occurred in different regions, and only a few, those producing three large dimensions, led to stable, long-lived universes. We observe three dimensions not because they're uniquely special, but because unstable alternatives didn't persist long enough to produce observers. This selection-based explanation leaves many uneasy. It feels like giving up on finding a unique solution. But it might be the truth. Perhaps the universe doesn't select a single answer but explores many, and we inhabit one of the stable outcomes. Compactification, then, isn't fully determined by physics alone, but by physics plus cosmic history, plus the requirement of stability. In the late 1990 seconds, theoretical physics underwent a quiet revolution. Physicists realized that string theory contained not just strings, but entire families of higher dimensional objects. These objects, called brains, short for membranes, transformed how we think about the universe and our place within it. String is one-dimensional. It has length but no width or thickness. But the mathematics of string theory revealed that two-dimensional membranes also exist naturally. So do three-dimensional volumes, four-dimensional hypervolumes, and so on. These are called two brains, three brains, four brains, extending all the way up to 9 brains in 10-dimensional string theory. The turning point came with a radical proposal. What if our entire observable universe is a three-brain? What if everything we know, every particle, every force except gravity, every atom and star and galaxy, is confined to a three-dimensional surface floating in higher dimensional space? This is the brain world scenario. We're not living in the full higher dimensional reality. We're stuck on a brain, like drawings on a sheet of paper, perceiving only the surface we inhabit. We can move freely in the three dimensions of our brain, but we cannot step off it into the extra dimensions beyond. The higher dimensional space surrounding our brain is called the bulk. It's the full 10 or 11-dimensional arena in which brains exist. The bulk is vast, extending in directions we cannot access. And crucially, gravity, unlike other forces, can propagate through it. This offers an elegant explanation for gravity's weakness. Electromagnetism, the strong force, and the weak force are confined to our brain. Their influence stays concentrated in our three dimensions, but gravity spreads into the bulk, diluting across the extra dimensions. What we perceive as gravity's feebleness is really just its influence being shared across a larger space. Imagine a drop of ink on a sheet of paper versus that same drop in a swimming pool. On the paper, the ink stays concentrated. In the pool, it disperses through the volume, becoming much less dense at any particular point. Gravity disperses into the bulk, while other forces stay concentrated on our brain. This idea, developed by Lisa Randall, Raman Sundram, and others, revolutionized thinking about extra dimensions. It meant the extra dimensions didn't all have to be compactified at the Planck length. Some could be much larger, perhaps even infinite without us noticing. as long as we're confined to our brain. In one version of the Randall-Sundrum model, there's a single extra dimension extending between two brains. Our observable universe is one brain. Another brain exists at some distance in the extra dimension, and the bulk curves in a special way that concentrates gravity near our brain, despite the extra dimension being potentially infinite. This warping of the bulk explains not only gravity's weakness, but also the hierarchy problem, why gravity is so much weaker than other forces. The hierarchy isn't fundamental but geometric, arising from how the bulk is curved between brains. The brain world picture also changes cosmology. If our universe is a brain, the Big Bang might not have been the beginning of everything, but just the beginning of our brain. Perhaps it formed from a collision with another brain drifting through the bulk. Perhaps multiple brains exist, each hosting its own universe with its own laws of physics. In these scenarios, parallel universes aren't just science fiction, they're geometric necessities. If the bulk exists and if brains form naturally in string theory, there's no reason to think ours is the only one. Other brains could exist, separated from ours by tiny distances in the extra dimensions, yet completely inaccessible to us because we can't leave our brain. These parallel brains might be very close micrometers away in the extra dimension, but we'd never know. We can't travel in that direction. We can't see across the gap. Only gravity, leaking into the bulk, might carry faint signals between brains. This leads to fascinating possibilities. What if dark matter is ordinary matter on a nearby parallel brain? We'd feel its gravitational influence but couldn't see it, because light is confined to brains. What if dark energy arises from interactions between our brain and others? What if the observed acceleration of cosmic expansion is caused by another brain pulling on ours gravitationally through the bulk? These ideas are speculative but testable in principle. If large extra dimensions exist, and if we're on a brain, there should be observable consequences. Gravity might deviate from the inverse square law at short distances. High-energy particle collisions might produce gravitons that escape into the bulk, appearing as missing energy. Collisions might even produce microscopic black holes if gravity becomes strong at small scales due to extra dimensions. The Large Hadron Collider searched for these signatures. None have been found, which constrains the models but doesn't rule them out entirely. It means that if large extra dimensions exist, they're smaller than initially hoped, or gravity doesn't strengthen as much as the simplest models predicted. Brains also provide new ways to think about black holes. In higher dimensions, black holes can be extended objects, black strings or black brains rather than points. A black string would look like a line of singularities extending through an extra dimension. A black brain would be a surface of singularities. If our universe is a brain, black holes in our space might be connected to structures in the bulk. The singularity at a black hole's center might be a point where our brain tears or connects to the bulk in a complicated way. Understanding black holes fully might require understanding the higher dimensional space they inhabit. Brains also connect to string dualities in deep ways. T-duality, which relates small and large compactified dimensions, can be understood as strings winding around brains. S-duality, which relates strong and weak coupling, involves transformations between different types of brains. The web of dualities, connecting string theories, becomes clearer when brains are included. From a mathematical perspective, brains are as fundamental as strings. In M-theory's 11-dimensional framework, membranes might be more basic than strings. Strings could emerge as special limits or boundaries of membranes. This suggests that what we call string theory might really be brain theory, with strings being just the one-dimensional case. The bulk itself is not merely empty space. It can contain fields, energy, even other brains. The geometry of the bulk can vary flat in some models, curved in others, warped in specific ways to achieve particular effects. Different bulk geometries lead to different physics on the brains they contain. Some models propose that the bulk is anti-de Sitter space, AS, a space with negative curvature. This connects to the famous ADS, CFT correspondence, which relates a gravitational theory in the bulk to a non-gravitational theory on the boundary. Our universe might be the boundary of such a space. With the bulk dynamics encoding everything we observe, Living on a brain changes how we think about fundamental questions. Where did the universe come from? Perhaps from brain nucleation in the bulk, a quantum fluctuation that created our brain. Why do physical constants have the values they do? Perhaps because they're determined by our brain's properties and its position in the bulk. The brain world picture is also philosophically striking. It resurrects an ancient idea that our reality might be a shadow or projection of something larger. Plato's cave allegory imagined people seeing only shadows on a wall, unaware of the three-dimensional world behind them. Brain suggests something similar. We observe three dimensions, unaware of the higher dimensional bulk beyond. But unlike Plato's metaphor, brain worlds are grounded in mathematics and potentially testable. They're not philosophical speculation, but consequences of trying to unify gravity with quantum mechanics in string theory and M theory. The turning point that brains represent is conceptual as much as technical. They shift the question from where are the extra dimensions to why can't we access them? The answer is that we're confined to a lower dimensional surface in a higher dimensional space. The dimensions exist all around us, but we're trapped on our brain, unable to step off into the bulk. This confinement might not be absolute. At extremely high energies, far beyond anything we can produce, particles might gain enough energy to leave the brain temporarily, explore the bulk, and return. Or perhaps quantum tunneling allows occasional excursions, but at accessible energies, we're stuck. The bulk remains a mystery. We can't observe it directly. We can only infer its properties from how our brain behaves, from gravitational effects, from the structure of string theory. We're like people in a submarine, exploring the ocean floor, never breaking the surface, but inferring from the currents and pressures that there's a vast, three-dimensional space above. And yet, the mathematics insists the bulk exists. It's required for consistency, for unifying forces, for explaining the hierarchy problem. Brainers and the bulk aren't decorative additions to physics. They're structural elements that make higher dimensional theories work. Whether we live on a brain is still unknown, but the idea has proven remarkably fruitful. Generating testable predictions, solving long-standing puzzles, and reshaping how physicists think about space, dimensions, and our place in the cosmos. One of the strangest and most profound ideas to emerge from modern physics is the holographic principle. It suggests that everything happening in a volume of space can be encoded on its boundary. The three-dimensional world we experience might be a projection, a hologram, arising from information stored on a two-dimensional surface. This isn't science fiction or mysticism. It's a serious proposal grounded in black hole physics and string theory, with mathematical support that has convinced many physicists it captures something fundamental about reality. The story begins with black holes. In the 1970 seconds, Jacob Bekenstein and Stephen Hawking discovered something unexpected. Black holes have entropy. Entropy measures disorder or information content. For ordinary objects, entropy scales with volume. The bigger the object, the more entropy it can contain. But black holes are different. Their entropy is proportional to the area of their event horizon, not their volume. A black hole with twice the radius has 4 times the area and 4 times the entropy, but 8 times the volume. It's as if the information content of a black hole is stored on its surface rather than throughout its interior. This was puzzling. Why would nature violate the usual volume scaling? Bekenstein suggested a radical answer. Perhaps the area law isn't special to black holes. Perhaps it applies everywhere. Perhaps the maximum information any region can contain is determined by its surface area, not its volume. In the 1990 seconds, Gerard Hooft and Leonard Susskind formalized this into the holographic principle. They proposed that the physics in any region of space can be described by a theory living on the boundary of that region with one fewer dimension. The interior isn't fundamental, it emerges from the boundary. Think of a hologram on a credit card. It's a two-dimensional image, but when light hits it correctly, a three-dimensional image appears. The 3D structure is encoded in the 2D surface. The holographic principle suggests reality works similarly. Our three-dimensional space might emerge from information encoded on a two-dimensional boundary. This seems impossible. How can 3 dimensions of experience, depth, solidity, volume come from a flat surface? But the mathematics suggests it's not only possible but necessary if we want to understand quantum gravity. The breakthrough came in 1997 with Juan Maldacena's ADS, CFT, correspondence. Maldacena showed that a specific type of gravitational theory in 5-dimensional anti-de Sitter space, ADS, is exactly equivalent to a quantum field theory without gravity living on the 4-dimensional boundary of that space. 2 completely different looking theories, one with gravity and extra dimensions, one without gravity and fewer dimensions, describe exactly the same physics. Everything happening in the 5-dimensional bulk can be computed from the 4-dimensional boundary theory and vice versa. This is holography made concrete. The 5-dimensional space emerges from the 4-dimensional boundary. Gravity in the bulk corresponds to interactions on the boundary. Black holes in the bulk correspond to thermal states on the boundary. The extra dimension isn't fundamental but a useful way of organizing information from the boundary theory. ADS, CFT has become one of the most important tools in theoretical physics. It allows calculations in strongly interacting quantum systems by translating them into gravitational problems in higher dimensions, where the math is more tractable. It's been applied to quark-gluon plasmas, condensed matter systems, even fluid dynamics. But beyond its practical uses, ADS, CFT, reveals something profound. Dimensions might be emergent rather than fundamental. The bulk dimension exists from one perspective, doesn't exist from another. Yet both perspectives describe the same reality, which is real, the 5-dimensional bulk or the 4-dimensional boundary. The answer is both, or neither. They're dual descriptions of the same underlying physics. This duality suggests that asking, how many dimensions does the universe have, might be like asking, is light a wave or a particle? The answer depends on how you look at it. From one mathematical description, there are more dimensions, from another, fewer. The true fundamental structure might not be dimensional at all, but something deeper from which dimensions emerge. Holography also connects to quantum entanglement in striking ways. In 2006, Shinsei Ryu and Tadashi Takayanagi discovered a formula relating entanglement entropy in the boundary theory to the area of surfaces in the bulk. The amount of quantum entanglement between regions on the boundary corresponds geometrically to minimal surfaces extending into the bulk. This suggests that spacetime geometry itself arises from entanglement. The connectivity of space, the fact that one point is next to another, that you can move smoothly from here to there, might be a consequence of quantum correlations. Without entanglement, space would fall apart into disconnected pieces. Mark van Ramsdonk and others have explored this idea, showing that cutting entanglement in the boundary theory corresponds to tearing apart the bulk spacetime. Space is woven from entanglement. Dimensions emerge when quantum information is organized in specific patterns. This perspective radically changes how we think about reality. Space, time, and dimensions might not be fundamental building blocks but emergent phenomena, like temperature or pressure. They appear at certain scales when underlying quantum information is arranged in particular ways. If true, this resolves the conflict between quantum mechanics and general relativity. General relativity treats spacetime as fundamental, continuous, and smooth. Quantum mechanics treats it as background for quantum fields. But if spacetime emerges from quantum information, both perspectives are approximations. The true fundamental description is neither geometric nor quantum mechanical in the usual sense, but something that gives rise to both. Holography also has implications for information and black holes. When a black hole evaporates through Hawking radiation, what happens to the information about what fell in? Hawking initially argued it was lost, violating quantum mechanics' unitarity, but holography suggests information is never truly inside the black hole, it's encoded on the horizon. When the black hole evaporates, the information returns in the radiation, scrambled but not lost. This black hole information paradox has driven decades of research. Holography provides a framework for resolution. Information isn't in the bulk, but on the boundary, so it can't be lost when the bulk changes. The paradox arises from taking the bulk description too literally. For our question about dimensions, holography is consequential. It means dimensions might not be countable features of reality, but contextual descriptions. In the boundary theory, there's no extra dimension, space is four-dimensional. In the bulk theory, space is five-dimensional. Both descriptions are valid and equivalent. This ambiguity extends to our universe. Some physicists speculate that our three-dimensional space might be holographic, emerging from information on a two-dimensional surface at the universe's boundary. Perhaps its cosmological horizon. If so, depth, volume, the interior of objects, all of it would be projections from a distant surface. This sounds bizarre. How could you be a projection? But holography doesn't mean you're an illusion. It means there's another equally valid description where you're encoded differently, in fewer dimensions. Both descriptions are real, they're just different mathematical languages for the same physics. Testing holography is difficult. ADS, CFT applies to anti-de Sitter space, which isn't quite like our universe, which is closer to de Sitter space with positive curvature. Extending holography to realistic cosmologies is an active research area. Some propose looking for signatures in the cosmic microwave background, subtle correlations that might reveal holographic structure. Others study analog systems. Quantum simulations and condensed matter systems can exhibit holographic behavior, providing labs for testing holographic principles. While these aren't direct tests of cosmic holography, they demonstrate that holography is real physics, not just mathematical abstraction. The consequence of holography for dimensions is profound. The number of dimensions might not be fixed, but dual, observer-dependent, emergent. Asking how many dimensions are real, it becomes like asking which description is real when multiple equivalent descriptions exist. This doesn't make dimensions less important or less real in experience. You still navigate three spatial dimensions, objects still have volume, physics in three dimensions still works. But fundamentally, dimensionality might be a feature of how we describe reality, not a feature of reality itself. Holography suggests the universe is more like information than like stuff, more like a description than like an object. And in that informational structure, dimensions are patterns of organization, not fixed scaffolding. This is perhaps the deepest revelation of modern physics, that the stage space, time, dimensions might not be fundamental but emergent, arising from quantum information arranged in ways we're only beginning to understand. Holography also reframes the question of quantum gravity. If space-time emerges from entanglement in information, then quantum gravity isn't about quantizing a pre-existing space-time, but about understanding how space-time crystallizes from quantum correlations. The problem shifts from how do we describe quantum fields on a curved background to how does the background itself emerge from quantum degrees of freedom? This is a much deeper, harder question, but also potentially more fundamental. Some approaches, like loop quantum gravity and causal set theory, pursue this by discarding continuous spacetime at small scales and replacing it with discrete structures from which geometry emerges. Others, like the ER equals EPR conjecture, propose that quantum entanglement and spacetime geometry are two sides of the same coin, that entangled particles are connected by tiny wormholes. All these ideas share holography's insight. Geometry is derived, not fundamental. Dimensions emerge, and the question, how many dimensions, has no single answer but depends on which level of emergence you're examining. There's a place where all our theories meet, where general relativity and quantum mechanics must both apply, where spacetime curvature and quantum uncertainty can't be separated. That place is the realm of quantum gravity inside black holes, at the Big Bang, at scales of 10, -35 meters, where space itself becomes grainy and uncertain. And in that realm, the question of how many dimensions the universe has becomes not just interesting but crucial, because it's precisely there where both gravity and quantum effects matter that our four-dimensional picture breaks down. General relativity describes gravity beautifully at large scales. Planets orbit, galaxies rotate, gravitational waves ripple through space-time. The theory treats space-time as a smooth, continuous fabric that curves in response to mass and energy. Quantum mechanics describes particles beautifully at small scales. Electrons orbit nuclei. Photons interfere with themselves. Particles tunnel through barriers. The theory treats space and time as fixed backgrounds on which quantum fields fluctuate. Both theories are extraordinarily successful. General relativity has been tested with exquisite precision, from GPS satellites to gravitational wave detections. Quantum mechanics underlies all of modern technology, from transistors to lasers to quantum computers, but the theories are fundamentally incompatible. When you try to apply quantum principles to gravity, to treat spacetime itself as a quantum field, the math explodes. Calculations produce infinities that can't be removed. Predictions become meaningless. This is the challenge of quantum gravity, and it's where the question of dimensions becomes critical. At everyday scales, the conflict doesn't matter. Gravity is so weak that you can ignore it when studying atoms. Quantum effects are so tiny that you can ignore them when studying planets. The theories operate in separate domains, but at the Planck scale, about 10, -35 meters, where both quantum effects and gravitational effects are strong, you can't ignore either. You need a unified framework, and that framework might require rethinking dimensions. Several approaches suggest that dimensions themselves become uncertain or variable at the Planck scale. In loop quantum gravity, space is not continuous but quantized, made of discrete loops of gravitational field. These loops weave together into a network called a spin network. Geometry emerges from their connections, not from a smooth background. In this picture, dimensions are properties of the network at large scales. Zoom in to the Planck scale, and the network becomes discrete, grainy. The concept of dimension loses clear meaning. You can't draw smooth coordinate axes through discrete nodes. Space doesn't have a full, well-defined dimensionality at the smallest scales. Interestingly, calculations in loop quantum gravity suggest that at very high energies, the effective number of dimensions drops. Space might behave as two-dimensional near the Planck scale, then gradually transition to 3 dimensions at larger scales. This dimensional reduction isn't imposed, but emerges from the theory's dynamics. Other approaches find similar results. Causal dynamical triangulations build spacetime from tiny simplices, higher dimensional analogues of triangles. By assembling these building blocks according to rules preserving causality, researchers simulate quantum spacetime. And what emerges is startling. The effective dimensionality changes with scale. At very small distances, spacetime appears two-dimensional. At intermediate scales, it transitions through non-integer dimensionality fractals, essentially. At large scales, it settles into 4 dimensions. This suggests that 4 dimensions aren't fundamental, but emerge at low energies. The underlying quantum structure might have different effective dimensionality depending on the scale you probe. String theory and M theory suggest something similar but from a different angle. While they require 10 or 11 dimensions fundamentally, the effective dimensionality we observe depends on compactification, and the compactification itself might be dynamic, changing with energy or evolving over cosmic time. Perhaps in the very early universe, all dimensions were equally large. As the cosmos expanded and cooled, some compactified, while others remained extended. The 3 spatial dimensions we observe emerged from this process, not as fundamental features but as consequences of how the universe evolved. The challenge of quantum gravity also manifests in black hole physics. At a black hole center, general relativity predicts a singularity, a point where curvature becomes infinite. But infinities signal that a theory has reached its limits. Quantum gravity should smooth out the singularity, replacing it with something finite but exotic. What that something is depends on how many dimensions are involved. In 4-dimensional quantum gravity, the singularity problem is notoriously hard. In higher dimensions, with strings or branes, new possibilities open. The singularity might be a region where strings become highly excited, where branes intersect, or where higher dimensional structure becomes important. Black hole entropy also points toward quantum gravity, involving extra dimensions. The entropy equals 1/4 the horizon area in Planck units. String theory reproduces this result by counting quantum states of strings and branes wrapping around compactified dimensions near the horizon. The calculation requires extra dimensions. 4 alone aren't enough. The cosmic microwave background offers another window. In the first instance after the Big Bang, quantum fluctuations were stretched to cosmic scales by inflation. These fluctuations left imprints in the CMB tiny temperature variations that we observe today. If quantum gravity involves extra dimensions, those dimensions might have affected the fluctuations. The pattern of hot and cold spots could carry signatures of higher dimensional physics. Observations haven't revealed such signatures definitively, but they constrain possibilities and guide theorists. Gravitational waves from the early universe, if detected, would probe even closer to the Planck epoch. These primordial waves would carry information about spacetime's quantum structure, potentially revealing whether dimensions were different then, whether compactification was underway, whether the universe passed through higher dimensional phases. The challenge of quantum gravity is also philosophical. What does it mean for dimensions to be uncertain or emergent? If space itself is quantized, if smooth geometry breaks down, what replaces our intuitive picture of dimensions as axes through continuous space? One answer is that dimensions are collective phenomena. Just as temperature emerges from molecular motion, it's meaningless for a single molecule but well-defined for many dimensions might emerge from collective behavior of quantum degrees of freedom. At the fundamental level, reality might not be spatial at all but described by abstract quantum states. Geometry and dimensionality emerge when many states are correlated in specific patterns. This has implications for causality, time, and the arrow of time. If space emerges from quantum information, time might too. The flow of time might not be fundamental but statistical, arising from increasing entanglement or entropy. The past is distinguished from the future, not by a fundamental time direction but by correlations among quantum states. These ideas remain speculative. No experiment directly probes the Planck scale. No observation conclusively demonstrates that dimensions change with energy, but multiple approaches string theory, loop quantum gravity, causal sets. Holography independently suggests that dimensions aren't fixed but contextual, emergent, scale-dependent. The impact of quantum gravity on the dimension question is profound. It suggests that asking, "How many dimensions are there?" is too simple. The answer depends on scale, energy, how you measure, what formalism you use. At large scales, 4 dimensions, 3 spatial, 1 temporal, describe reality. At the Planck scale, dimensionality might fluctuate, reduce, or dissolve into something more fundamental. This doesn't make our 4-dimensional experience less real. Emergence doesn't mean illusion. Temperature is real and important, even though it's not fundamental. Similarly, our 4-dimensional spacetime is real at the scales we inhabit, even if it emerges from deeper structure. The challenge is to understand that deeper structure. What are the fundamental degrees of freedom? How do they organize to create space and time? Why do 3 dimensions expand while others, if they exist, stay hidden? What physical principles govern dimensional emergence? These questions define the frontier of quantum gravity research, and they show that dimensions, far from being simple features of geometry, are deeply connected to the most fundamental puzzles in physics. The challenge also extends to experiments and observations. How can we test theories of quantum gravity when the relevant energy scales are so far beyond our reach? One approach is precision cosmology, looking for tiny deviations from standard predictions in the CMB or gravitational waves. Another is searching for modified gravity at small scales or high energies. A third is studying analog systems, quantum simulations, or condensed matter systems that mimic quantum gravity effects. None of these are direct observations of Planck-scale physics, but they provide constraints and hints. Perhaps most importantly, the mathematical consistency of quantum gravity theories offers a guide. If only certain numbers of dimensions allow consistent quantum gravity, that's a form of theoretical evidence. Not as strong as experimental confirmation, but meaningful nonetheless. The challenge of quantum gravity is both a technical problem and a conceptual one. It requires new mathematics, new experimental techniques, and new ways of thinking about space, time, and dimensionality. But meeting this challenge is essential, because without quantum gravity, we can't fully understand black holes, the Big Bang, or the ultimate structure of reality. And the dimension question sits at the heart of that understanding. There's something deeply human about wanting to understand dimensions. We navigate space instinctively, reaching for objects, judging distances, moving through rooms. Our entire sensory apparatus evolved to map three-dimensional reality. But there's also something human about transcending those instincts, using mathematics to explore what senses cannot reach. And in that exploration, one of the strangest quantum phenomena, entanglement, might hold the key to understanding how dimensions themselves arise. Quantum entanglement was famously called spooky action at a distance by Einstein, who was deeply troubled by it. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. It's not that a signal travels between them, nothing moves faster than light. Rather, the two particles share a quantum state. They're not separate entities, but parts of a unified whole. This phenomenon has been verified countless times in laboratories. Entangle two photons, send one to Tokyo and one to New York, measure one, and the other's state changes instantaneously. The correlation is perfect, immediate, and deeply strange. But what does this have to do with dimensions? In recent years, physicists have discovered that entanglement might not just connect particles, it might create space itself. The geometry of spacetime, the connectivity that makes one point adjacent to another, might emerge from patterns of quantum entanglement. This idea arose from studying the AD-CFT correspondence. In 2006, Shinsei Ryu and Tadashi Takeyanagi derived a formula relating entanglement entropy in the boundary quantum field theory to the area of surfaces in the bulk spacetime. The more entangled two regions are on the boundary, the shorter the geometric distance between corresponding points in the bulk. This wasn't just a mathematical curiosity. It suggested something profound, that geometry is entanglement. The fabric of spacetime, the structure that gives rise to dimensions, might be woven entirely from quantum correlations. Mark van Ramsdonk explored this further, showing that if you reduce entanglement between regions in the boundary theory, the bulk spacetime tears apart. Cut the entanglement completely, and the space disconnects. Restore the entanglement, and space reconnects. Entanglement is the glue holding space together. Think about what this means. You experience space as something solid, external, independent of observers. But if Van Ramsdonk is right, that solidity is an illusion. Space exists because quantum information is entangled in specific patterns. Remove the entanglement, and space dissolves. This perspective transforms how we think about dimensions. Dimensions aren't primary features of reality, but emergent patterns arising when quantum systems are correlated in particular ways. The three spatial dimensions we navigate exist because the quantum state of the universe has a specific entanglement structure. Different entanglement patterns could produce different dimensionalities. In the early universe, when quantum states were less organized, dimensionality might have been unclear or variable. As the universe evolved and cooled, entanglement patterns stabilized, crystallizing the three dimensions we observe. Juan Maldacena took this further with the ER equals EPR conjecture. ER refers to Einstein-Rosen bridges, wormholes connecting distant regions of spacetime. EPR refers to Einstein-Podolsky-Rosen pairs entangled particles. The conjecture proposes they're the same thing. Entangled particles, according to ER equals EPR, are connected by tiny wormholes. The quantum correlation we call entanglement is geometrically realized as a tunnel through spacetime. Two particles aren't mysteriously connected across space. They're connected through space, via a microscopic wormhole too small to send signals but real nonetheless. If true, this means entanglement and geometry are two languages for describing the same reality. When quantum mechanics talks about entanglement, General relativity talks about space-time connectivity. They're not separate phenomena, but different perspectives on how the universe is stitched together. This has human resonance. We've always wondered how things connect, how we connect to each other, to the cosmos, to the past and future. Quantum entanglement and space-time geometry offer answers, not metaphorical but mathematical. Connection is fundamental. It's woven into reality at the deepest level, and it's what creates dimensions. Without entanglement, no connectivity. Without connectivity, no space. Without space, no dimensions. The very framework we inhabit emerges from quantum correlations. This also suggests why gravity is special. Gravity, unlike other forces, is intimately tied to space-time geometry. In general relativity, gravity is the curvature of space-time. If space-time emerges from entanglement, then gravity emerges too. It's not a force in the usual sense, but a manifestation of how entanglement organizes itself geometrically. Other forces, electromagnetism. The strong and weak forces operate within space-time. They're defined on the spatial structure. But gravity is the spatial structure. It's the geometry itself, which is why it's been so hard to quantize. You can't treat space as background, when space is what you're trying to describe. Entanglement offers a way forward. If space emerges from entanglement, quantum gravity becomes the study of how entanglement patterns give rise to geometry. Instead of quantizing a pre-existing spacetime, you derive spacetime from quantum states. The problem transforms from how do we describe quantum fields on curved space to how does space emerge from quantum information? This shift is profound. It suggests the universe isn't fundamentally spatial but informational. Space, time, and dimensions are high-level descriptions that emerge when quantum information is organized appropriately. There's something beautiful about this view. Information has no inherent dimensionality. A quantum state can encode arbitrary correlations without reference to space. But when those correlations take specific forms, when entanglement follows certain patterns, spatial structure emerges. Dimensions crystallize from information. This connects to consciousness and perception in interesting ways. We experience 3 spatial dimensions because our brains evolved to extract spatial information from sensory data. But the underlying reality might not be spatial at all. It might be a network of quantum correlations from which our brains construct the illusion of 3-dimensional space. This doesn't mean space is an illusion in a dismissive sense. The construction is real and functional. It accurately captures relationships in the quantum state, but it's a constructed model, not the fundamental layer. Similarly, entanglement suggests that connection, quantum correlation, is more fundamental than separation. Things appear separate in space, but that separation emerges from how we slice the underlying quantum state into pieces. At the deepest level, everything is connected through patterns of entanglement. This resonates with ancient philosophical intuitions about unity underlying apparent multiplicity. But here, it's not mysticism, it's mathematics. The equations of quantum mechanics and general relativity, when properly understood, point towards space emerging from non-spatial quantum correlations. Experimental hints are beginning to accumulate. Studies of quantum systems show that entanglement structure correlates with effective spatial relationships. Systems with high entanglement behave as if they're spatially close, even if they're physically distant. Systems with low entanglement behave as if they're distant, even if they're near. In condensed matter physics, some materials exhibit emergent spacetime. Their collective excitations behave like particles moving through an effective curved space, even though the underlying lattice is flat. This demonstrates that spacetime can emerge from non-spatial degrees of freedom. These are analogies, not direct observations of cosmic entanglement creating space. But they show the principle is sound. Entanglement can generate effective geometry. Scale that up to the universe, and you have a mechanism for dimensional emergence. The human element in all this is our growing understanding that reality is stranger than appearances. We evolved to perceive 3 dimensions, to feel that space is primary. But deeper investigation reveals that space might be derivative, emerging from quantum information in ways we're only beginning to grasp. This is humbling but also empowering. It shows that human intellect can transcend evolutionary limitations. We can discover truths about reality that our senses never reveal, using mathematics as a tool for seeing beyond perception. Entanglement weaving space is one of those truths. It suggests that dimensions aren't given but constructed, not fundamental but emergent, not separate but arising from connection. And in that emergence, we glimpse how the universe builds itself from quantum information into the spatial reality we inhabit. The connection between entanglement and space also changes how we think about quantum measurement. When you measure a particle, you become entangled with it, your quantum state, and the particles become correlated. This entanglement isn't just abstract information. If Van Ramsdonk and others are right, it's a geometric connection, a thread of spacetime linking you to the particle. Observation becomes participation in spacetime structure. This dissolves the boundary between observer and observed in a concrete physical way. You're not separate from what you measure. You're entangled with it, connected through the same quantum correlations that create space itself. This makes measurement an act of connection rather than passive observation. And it suggests consciousness, to the extent it involves measurement and correlation, is woven into the fabric of space-time through entanglement. These are speculative thoughts, extending physics into philosophy. But they're grounded in real mathematics, real discoveries about how entanglement and geometry relate. The human element is recognizing that we're not separate from the dimensional structure we study. We're part of it, created by it, connected through it. For all the mathematical elegance of extra dimensions, for all the theoretical necessity they seem to provide, there remains a stubborn fact. We haven't seen them. Every experiment, every observation, every measurement confirms that space appears three-dimensional and time one-dimensional. 4 dimensions total, no more. This is the opposition that theories of extra dimensions face. Not hostile opposition. Physicists would be thrilled to detect higher dimensions, but the opposition of reality's apparent simplicity against theory's complexity. The limits we face are both practical and fundamental. Practically, probing scales where extra dimensions might reveal themselves requires energies far beyond what we can produce. The Planck length, where quantum gravity effects and dimensional structure become important, is 10⁻35 meters. The smallest distances we can probe with particle colliders are about 10⁻19 meters, 16 orders of magnitude too large. It's like trying to study atoms with a microscope that can only resolve millimeters. You know atoms exist theoretically, but you can't see them directly with available tools. Similarly, we know string theory and M theory predict extra dimensions, but we can't access them with current technology. This creates a credibility problem. If a theory predicts things that can never be tested, is it science or mathematics? Physics has always distinguished itself from pure mathematics by requiring experimental verification. Theories must make testable predictions, or they remain speculative. String theory and its extra dimensions make precise mathematical predictions, but almost all occur at the Planck scale. We can calculate exactly how strings should behave, what particle masses should be, how forces should unify, but only at energies 15 times higher than the Large Hadron Collider can reach. Some physicists argue this puts string theory outside the domain of science. Without testability, it's an elegant mathematical framework, but not a physical theory. This criticism has force. Science progresses through experiment. Pure mathematics, however beautiful, isn't enough. Defenders respond that indirect tests are possible. String theory makes connections to black hole physics, cosmology, quantum information theory. It suggests mechanisms for inflation, explanations for dark matter, relationships between seemingly unrelated phenomena. These aren't direct observations of strings or extra dimensions, but they're scientific touchstones. Moreover, the theory's consistency is itself a kind of evidence. The fact that string theory requires exactly 10 dimensions, that anomalies cancel precisely in that dimensionality, that gravity emerges automatically, these suggest the theory captures something real about nature, even if we can't probe it directly yet. But the opposition remains. Other physicists pursue different approaches to quantum gravity loop, quantum gravity, causal sets, asymptotic safety that don't require extra dimensions. These alternatives work in 4 dimensions, adding structure at small scales rather than extending into higher ones. Loop quantum gravity, for instance, quantizes space itself, creating a discrete network of quantum geometric relationships. It achieves some of what string theory does a quantum description, including gravity without adding dimensions. This shows extra dimensions aren't the only path to quantum gravity. The existence of alternatives raises questions. If multiple frameworks can address the same problems, how do we choose? Usually, experiments decide. But when all approaches make predictions at inaccessible scales, experiment can't adjudicate. We're left with criteria like mathematical consistency, elegance, connection to known physics, subjective measures that different physicists weight differently. This is uncomfortable. Physics prides itself on objectivity, on letting nature decide through experiment. But at the frontiers, when experiments can't reach, the field resembles philosophy or mathematics more than classical experimental science. This doesn't invalidate the work. Mathematical consistency is a real constraint, but it changes the character of the enterprise. The limits we face are also conceptual. Even if extra dimensions exist, understanding what that means is difficult. Compactified dimensions curled at the Planck scale are so far from experience that it's unclear what existence means in this context. Does a dimension exist if nothing can move through it macroscopically? If no experiment can detect it? If its only effects are in the mathematical structure of theories? These aren't idle questions, they go to the heart of what we mean by real. Some argue that mathematical necessity equals physical reality. If the equations demand extra dimensions, they exist, regardless of direct observability. This view treats mathematics as the ultimate arbiter of reality. Others insist that without observational consequences, dimensions remain hypothetical. They might be useful calculational tools without corresponding to anything physical. This view prioritizes empiricism over mathematical elegance. The truth might lie between these extremes. Extra dimensions might exist but manifest only in subtle, indirect ways, through gravity's weakness, through particle properties, through cosmological signatures. Finding those manifestations requires cleverness in designing experiments and observations. But the limits are real. We can't build colliders powerful enough to reach the Planck scale. It would require energy densities that would themselves create black holes. We can't directly observe compactified dimensions smaller than any probe we could construct. We can't travel into the bulk or see parallel brains. These aren't temporary technological limitations, but fundamental ones. The scales involved are so extreme that direct observation may be impossible in principle, not just in practice. This forces physicists to be creative. Look for missing energy in collisions, suggesting particles escaping into extra dimensions. Look for deviations from the inverse square law at short distances, suggesting gravity spreading into hidden spaces. Look for patterns in the cosmic microwave background, suggesting dimensional structure in the early universe. So far, these searches have come up empty. The inverse square law holds down to sub-millimeter scales. No missing energy has been conclusively detected. The CMB fits standard 4-dimensional cosmology well. Each null result constrains the theories. If large extra dimensions existed at millimeter scales, we would have seen gravity's behavior change. We haven't, so if extra dimensions exist, they're smaller. If supersymmetric particles exist at low energies, we should have found them at the LHC. We haven't, so if they exist, they're heavier than expected. The absence of evidence isn't evidence of absence, but it is information. It narrows the parameter space, makes theories work harder to accommodate observations, pushes predictions to less accessible regimes. Some physicists find this discouraging. Decades of theoretical work on extra dimensions haven't produced experimental confirmation. Resources have been invested in building colliders and detectors specifically to search for signatures of new physics, and nothing unexpected has appeared. Others see it as normal science. Theories make predictions, experiments test them, and if predictions fail, theories are refined or replaced. That's how physics progresses. The fact that extra dimensions haven't been confirmed yet doesn't mean they won't be eventually, or that searching was wrong. The opposition extra dimensions face is the same. Opposition all bold theoretical ideas face. Show me. Physics is grounded in observation. Without observational support, theories remain provisional, however mathematically beautiful. This tension between mathematical elegance and empirical verification defines modern fundamental physics. We're exploring regimes where experiments are difficult or impossible, where mathematics guides us, but nature doesn't immediately confirm or deny our ideas. The limits we face are humbling. They remind us that nature doesn't care about our theories, that reality is what it is regardless of what we'd like it to be. Extra dimensions might exist, or they might be artifacts of how we've formulated our theories useful mathematically but not physical. Only continued observation, more precise experiments, and perhaps breakthrough insights will resolve the question. For now, the opposition stands. Extra dimensions are theoretically motivated but empirically unconfirmed. The limits of our technology and perhaps of physics itself prevent us from seeing beyond the 4 dimensions we know. The opposition also comes from within the physics community itself. Not all physicists accept that extra dimensions are necessary or likely. Some argue that the problem string theory solves quantum gravity. Force unification might have 4-dimensional solutions we haven't discovered yet. Perhaps we're not clever enough, and adding dimensions is taking an easier mathematical path rather than finding the true 4-dimensional answer. Others point to the landscape problem, the vast number of possible string theory vacua, and argue that a theory predicting 500 different possible universes predicts nothing at all. If any observation can be accommodated by choosing the right vacuum, the theory has no falsifiability. This criticism is sharp and difficult to answer. String theorists respond that we might eventually understand vacuum selection, that anthropic reasoning might constrain possibilities, or that the multiverse might be real with different regions realizing different vacua. But these responses feel less satisfying than a unique prediction verified by experiment. The opposition, then, isn't just nature refusing to show extra dimensions, but the scientific community debating whether the whole framework is the right path. This debate is healthy. It keeps physicists honest, prevents groupthink, and ensures alternative approaches continue to be developed. But it also means extra dimensions remain contested ground. Despite the challenges, the search for extra dimensions continues. Physicists are remarkably creative when faced with seemingly impossible observational problems. If you can't see something directly, look for its shadows, its influences, the effects it has on things you can see. This is the awakening, the recognition that while extra dimensions might hide, they can't hide perfectly. If they're real, they must affect observable physics somehow. Even if subtly, the search takes many forms, each targeting different potential signatures. Particle colliders remain a primary tool. The Large Hadron Collider at CERN smashes protons together at energies around 13 TeV, tera-electron volts. While this is far below the Planck energy, about 19 GeV, it's high enough to potentially reveal hints of extra dimensions if they manifest at lower scales than expected. One signature would be missing energy. If particles can escape into extra dimensions during high-energy collisions, the total energy of observed decay products wouldn't match the initial energy. It would look like energy disappeared, not lost to measurement error, but genuinely vanishing into hidden dimensions. Gravitons are the prime candidates. If gravity spreads into extra dimensions, then high-energy collisions might produce gravitons that immediately escape into the bulk, appearing as missing transverse momentum in detectors. Physicists have searched extensively for such events. None have been conclusively found, but the searches continue with increasingly sophisticated analysis. Another collider signature would be Kaluza-Klein excitations, heavy versions of known particles arising from momentum in compactified dimensions. These would appear as resonances at specific energies, peaks in the data where particle production rates jump. The LHC has searched for KK excitations of photons, Z bosons, gravitons, and other particles. So far, nothing. Each null result pushes the constraints tighter. If KK excitations exist, they're heavier than we've probed. If extra dimensions exist, they're smaller than various models predicted. The parameter space shrinks, but space remains. Some scenarios propose large extra dimensions much larger than the Planck length, perhaps even millimeter scale. In these models, gravity appears weak because it dilutes into these large extra dimensions while other forces stay confined. If true, gravity should deviate from the inverse square law, at distances comparable to the extra dimension size. Experiments test this using torsion balances, extremely sensitive devices, measuring gravitational attraction between masses at short distances. Current tests confirm the inverse square law down to about 50 micrometers. If extra dimensions are larger than this, we would have seen deviations. We haven't, so if large extra dimensions exist, they're smaller than 50 micrometers. Future experiments will probe shorter distances, potentially down to a few micrometers. These are tabletop experiments, far smaller than the LHC, but equally important for constraining extra-dimensional models. Gravitational waves offer another avenue. When massive objects like black holes or neutron stars merge, they send ripples through spacetime gravitational waves. LIGO and Virgo have detected dozens of these events since 2015, measuring the wave's properties with extraordinary precision. If extra dimensions exist, gravitational waves might behave differently than general relativity predicts in 4 dimensions. They might travel at slightly different speeds, decay faster, losing energy into extra dimensions, or exhibit polarizations not present in 4-dimensional gravity. The 2017 observation of gravitational waves from a neutron star merger, detected simultaneously with gamma rays, showed that gravitational waves travel at the speed of light to within 1 part in 10, 15. This ruled out many modified gravity theories and constrained extra-dimensional models that predicted different propagation speeds. Future gravitational wave detectors LISA in space, Einstein telescope and Cosmic Explorer on the ground will be more sensitive, detecting waves from earlier in cosmic history and from more distant sources. These observations might reveal subtle extra-dimensional effects invisible to current detectors. Cosmology provides additional tests. The cosmic microwave background, the afterglow of the Big Bang, carries information about the universe's first moments. If extra dimensions were important during inflation or in the early universe, they should have left imprints in the CMB's temperature and polarization patterns. Physicists look for specific signatures. Non-Gaussianities, deviations from random noise, unexpected correlations between scales, anomalies in how matter fluctuations evolve. Observations from the Planck satellite and ground-based experiments have mapped the CMB exquisitely, finding patterns that match standard 4-dimensional cosmology well, but subtle deviations might still lurk in the data. As analysis techniques improve and new experiments achieve better sensitivity, hidden signals might emerge. The search continues. Dark matter offers another possibility. We know dark matter exists gravitationally. Its effects on galaxy rotation, gravitational lensing, and cosmic structure are undeniable. But we don't know what it's made of. Could dark matter be Kaluza-Klein particles? Heavy excitations from momentum in extra dimensions would interact very weakly with ordinary matter, since they differ in their KK quantum number, making them dark. They'd have the right properties to account for observed dark matter. Dozens of experiments search for dark matter particles directly through underground detectors, looking for rare collisions with ordinary matter, and indirectly through telescopes searching for gamma rays from dark matter annihilation. If dark matter is KK particles, these experiments might detect them or their byproducts. So far, no conclusive detections, though several intriguing hints have appeared and disappeared with more data. The search remains active, with new experiments continually coming online. Astrophysical observations also constrain extra dimensions. Supernova explosions, for instance, release enormous energy, primarily as neutrinos. If extra dimensions existed at accessible scales, some of this energy could escape into the bulk, making supernovae dimmer or changing their energy output. Observations of supernova 1987 are constrained extra dimensions through precisely such reasoning. The neutrinos arrived with properties matching four-dimensional predictions, limiting how much energy could have leaked into extra dimensions. Similarly, the cooling rates of white dwarfs and neutron stars constrain hidden dimensions. These objects cool by emitting photons and, if extra dimensions exist, potentially by radiating into the bulk. Observed cooling rates match predictions without bulk radiation, limiting extra-dimensional scenarios. Even tabletop quantum experiments contribute. Studies of quantum systems, ultra-cold atoms, trapped ions, quantum circuits sometimes reveal unexpected behaviors that could hint at new physics. While not designed specifically to detect extra dimensions, these experiments explore quantum mechanics in unprecedented detail, and anomalies could point toward higher dimensional effects. The awakening is the realization that evidence for extra dimensions, if it exists, will likely come from multiple converging lines of inquiry rather than a single dramatic discovery. No one experiment will definitively prove or disprove extra dimensions. Instead, many observations will gradually constrain possibilities, narrow parameter space, and perhaps reveal patterns consistent with higher dimensional physics. This is how science often works at the frontiers. Progress is incremental, building from many small pieces of evidence rather than single breakthroughs. The awakening to this reality makes the search more sophisticated, more patient, more comprehensive. And it continues. Every year, detectors improve. Every year, analysis techniques advance. Every year, the constraints tighten and the accessible parameter space shrinks. If extra dimensions exist within the reach of our growing capabilities, we'll eventually find them. If they don't, or if they're forever beyond reach, we'll know with increasing confidence that 4 dimensions suffice to describe observable reality. The search for evidence is the scientific process in action. Hypothesis, prediction, observation, refinement. Extra dimensions remain hypothetical, but the search for them is rigorous, creative, and ongoing. This is the awakening, recognizing that answers come not from armchair theorizing, but from looking, measuring, testing, from letting nature speak through experiments and observations. The awakening also includes theoretical developments that make extra dimensions more testable. New models propose signatures at lower energies, more distinctive patterns, connections to observable phenomena like dark energy or the cosmological constant. Physicists work to sharpen predictions, making them specific enough that experiments can confirm or rule them out. This interplay between theory and experiment drives progress. Theories suggest what to look for. Experiments constrain what's possible. Refined theories respond to constraints. Improved experiments test refined predictions. It's a dance, a dialogue between imagination and reality. The awakening is recognizing that this dialogue, not any single observation, is how we'll ultimately determine whether extra dimensions are real. It requires patience, persistence, and willingness to follow evidence wherever it leads. Some physicists dedicate entire careers to searching for extra dimensions without finding them. This isn't failure, it's science. Ruling out possibilities is as important as confirming them. The awakening is embracing that uncertainty, continuing the search not because success is guaranteed, but because the question matters, and the search is how we answer it. One of the most profound shifts in understanding dimensions comes from realizing that the question, how many dimensions are there, might not have a single answer. The number of dimensions might depend on the scale at which you probe reality. Changing with energy, with distance, with the resolution of your observations. This is the revelation of scale-dependent dimensionality. It's not that we're uncertain about the number, it's that the number itself is contextual, variable, emergent. Multiple approaches to quantum gravity independently suggest this conclusion. In causal dynamical triangulations, spacetime is built from tiny simplices geometric building blocks. Researchers simulate quantum spacetime by assembling these pieces according to rules that preserve causality. What emerges from these simulations is startling. At very small scales near the Planck length, spacetime appears two-dimensional. Not fuzzy or uncertain, clearly two-dimensional. The effective number of dimensions is 2. As you zoom out to slightly larger scales, dimensionality increases, passing through non-integer values, fractals. Essentially, space becomes intricate, crinkled, exhibiting self-similar structure at multiple scales. Finally, at large scales, the scales we inhabit dimensionality settles to 4. 3 spatial, 1 temporal. The smooth spacetime of general relativity emerges from the fractal quantum substrate. This dimensional flow is dynamic, a feature of how quantum spacetime behaves at different resolutions. It's not that extra dimensions compactify, it's that the effective dimensionality literally changes with scale. Loop quantum gravity finds similar results. Space is discrete at the Planck scale, made of quantum loops. The number of dimensions emerges from how these loops connect into networks. At small scales, the connectivity creates effectively fewer dimensions. At large scales, more. Even string theory, which fundamentally requires 10 dimensions, exhibits dimensional reduction in certain limits. Near horizons of black holes, in intense gravitational fields, the effective dimensionality can drop. The 10 dimensions aren't all equally accessible or important at every scale. This revelation transforms the dimension question. Instead of asking, how many dimensions are fundamental, we should ask, how many dimensions are effective at this scale? The answer for human experience is 4, 3 spatial, 1 temporal. At these scales, spacetime is smooth, continuous, well approximated by general relativity. Extra dimensions, if they exist, are hidden by compactification or confinement to branes. At collider energies probing down to 10, negative 19 meters, the answer might still be 4, or we might begin to see hints of more. Kaluza-Klein excitations, if they exist at these scales, would signal extra compactified dimensions. At the Planck scale 10, negative 35 meters, the answer might be 10 or 11 if string theory is correct, or 2 if dimensional reduction dominates, or something stranger if dimensions themselves become ill-defined in quantum foam. This scale dependence parallels other physical quantities. Temperature, for instance, is well defined for large systems but meaningless for individual particles. It emerges at certain scales, not others. Similarly, dimensions might be properties that emerge and transform as you change your observational resolution. This has philosophical implications. It means dimensions aren't absolute features of reality but relative to how you observe. Not subjective or arbitrary, the mathematics is precise but contextual. The universe doesn't have a single, definitive dimensionality independent of scale. It also explains why different theoretical approaches can require different numbers of dimensions. String theory needs 10 because that's the dimensionality where strings consistently vibrate. M theory needs 11 to unify string theories. Loop quantum gravity works in 4 but finds 2 at small scales. These aren't contradictions, they're descriptions valid at different scales or in different limits. The revelation connects to renormalization in quantum field theory. Physical quantities like mass and charge depend on the energy scale at which you measure them. An electron's bare mass is different from its measured mass because quantum fluctuations contribute differently at different energies. Similarly, dimensionality might run with scale. The bare dimensionality at the Planck scale could differ from the effective dimensionality we observe. Spacetime itself renormalizes, with dimensions emerging or disappearing as you change your energy probe. This makes the question, what is the true number of dimensions? Ill-posed, like asking, what is the true temperature of a system, without specifying at what scale you're measuring? The answer depends on context. For practical purposes, 4 dimensions are true. They describe reality at human scales with extraordinary accuracy. Navigation, engineering, astronomy, all work beautifully with 3 spatial dimensions and 1 of time. For fundamental physics, attempting to describe quantum gravity and unify forces, more dimensions seem necessary. Whether they're fundamental or emergent, compact or extended, 10 or 11 or some other number, remains unclear. But scale-dependent dimensionality offers a framework for reconciling different answers. It also suggests that dimensional structure is dynamic, not static. Dimensions aren't a fixed stage, but an evolving feature of spacetime, changing with cosmic history, with local conditions, with quantum fluctuations. In the early universe, all dimensions might have been similar. As the cosmos expanded and cooled, dimensional structure crystallized, with some dimensions growing while others compactified or reduced. What we observe today, 4 dimensions, is a frozen accident, a particular outcome of cosmic evolution. Other regions of a larger multiverse might have frozen differently, 5 large dimensions, or 2, or varying numbers in different domains. We observe 4, because that's what our region selected, possibly because only 4-dimensional regions support the kind of complexity needed for observers. The revelation of scale-dependent dimensionality also reframes the search for extra dimensions. Instead of looking for additional fixed dimensions, we should look for signatures of dimensional flow changes in how space behaves at different scales. This might appear as deviations in particle physics at high energies, as anomalies in gravitational waves from extreme sources, as patterns in the CMB from the early universe when scales were different. The signatures would be subtle, not whole new dimensions opening up, but the effective dimensionality shifting slightly from expected values. Some quantum gravity approaches predict specific dimensional flow, how many dimensions at what scales. These predictions, when refined, could be testable. If observations match predicted flow patterns, it would be strong evidence that dimensions are indeed scale-dependent. The revelation is humbling and liberating. Humbling because it shows our familiar 4 dimensions aren't absolute truth but an emergent approximation. Liberating because it resolves apparent contradictions. Different theories requiring different dimensions can all be correct in their domains. It means the universe is richer than we imagined, not just spatially, with hidden dimensions, but structurally, with dimensionality itself being flexible, contextual, evolving. Reality isn't built on a fixed dimensional framework, but on something deeper that manifests different dimensionalities, depending on how it's probed. This revelation sits at the cutting edge of current research. It's not fully accepted. Many physicists still seek a single definitive answer to the dimension question, but the mathematics increasingly points towards scale dependence as essential, not incidental. And it suggests that progress in understanding dimensions will come not from finding the right number, but from understanding how dimensionality emerges, flows, and stabilizes across scales. That's a deeper question than simple counting, and answering it will require insights we haven't yet achieved. The revelation of scale-dependent reality also extends to time. Just as spatial dimensionality might vary with scale, the nature of time might too. At Planck scales, time might not be continuous but discrete, or it might emerge from something more fundamental: quantum correlations, causal relationships, thermodynamic arrow. At large scales, time flows smoothly, one-dimensional, with a clear path to future direction. But zoom in far enough, and that structure might dissolve. Some approaches to quantum gravity, like causal sets, build spacetime from discrete causal relationships, points connected by "this happened before that" links. Time and space both emerge from this causal structure. The number of dimensions isn't fundamental. It's derived from how causal links organize. This suggests a radical view. Perhaps nothing about spacetime is fundamental. Not dimensions, not continuity, not even the separation of space from time. All of it emerges from deeper, non-geometric structures, quantum states, information, causal relationships. We live at scales where this structure has crystallized into 4 smooth dimensions. But that's a contingent outcome, not an absolute truth. The revelation asks us to hold reality more lightly, to recognize that even the most basic features of our experience, up and down, here and there, now and then, might be emergent patterns rather than fundamental building blocks. This isn't disturbing once you accept it. It's an invitation to look deeper, to find what underlies even space and time. As we near the end of this exploration, it's worth stepping back and reflecting on what we've discovered. The question, how many dimensions does the universe have, has led us through relativity, quantum mechanics, string theory, holography, and entanglement. And the deeper we've gone, the less certain the answer becomes. Not because we're confused, but because the question itself might be based on a faulty assumption that dimensions are fundamental. What if they're not? What if dimensions, like temperature or pressure, are emergent properties that appear at certain scales but don't exist at the deepest level? This possibility emergence over fundamentals is one of the most important shifts in modern physics. It reframes how we think about reality's basic ingredients. For centuries, physics searched for fundamental objects. Atoms were supposed to be indivisible. Then we found they're made of electrons and nuclei. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks and gluons. At each level, we found structure beneath structure. And we kept asking, what's truly fundamental? What are the irreducible building blocks? String theory answers strings. M theory answers brains and membranes. Loop quantum gravity answers quantum loops of space. Each approach posits something fundamental from which everything else emerges. But increasingly, physicists suspect even these might not be fundamental. Perhaps there is no bottom, no final layer of truly elementary objects. Perhaps reality is like an onion with infinite layers, each revealing more structure beneath. Or perhaps the very question is wrong. Perhaps reality isn't built from objects at all, but from relationships, from information, from processes. And what we call fundamental is just the deepest layer we've currently reached, not an absolute foundation. Dimensions fit naturally into this emergent view. At human scales, 3 spatial dimensions and 1 of time emerge clearly. They're useful, accurate, descriptive. Physics formulated in 4 dimensions works brilliantly. At Planck scales, dimensions might dissolve into quantum foam, into discrete networks, into information patterns that don't have clear dimensional structure. Asking, how many dimensions are there? Becomes like asking, how many waves are in a turbulent fluid? Waves are real patterns, but they're not fundamental objects, they're collective behaviours of water molecules. Similarly, dimensions might be collective behaviours of quantum degrees of freedom patterns that emerge when you coarse-grain from microscopic to macroscopic, from Planck scale to human scale. This emergence explains why different theories require different numbers of dimensions. They're describing reality at different levels. String theory's 10 dimensions might be the effective description at certain energy scales. M theory's 11 might be the right count in certain limits. 4 dimensions are accurate at our scale. 2 might be effective near the Planck scale. None of these are absolutely right or wrong. They're all valid descriptions of the same underlying reality, which itself doesn't have a fixed dimensionality but exhibits different dimensional structure depending on how you probe it. This perspective is philosophically profound. It means the most basic features of reality, space, time, and dimensions, aren't given but constructed. They're high-level summaries of complex underlying dynamics, not the dynamics themselves. Think about consciousness as an analogy. Your subjective experience, qualia, thoughts, emotions, emerges from neurons firing in complex patterns. No single neuron is conscious. Consciousness appears only when billions of neurons interact in specific ways. It's real and important at its level, but it's not fundamental, it's emergent from neurobiology. Similarly, spacetime and its dimensions might emerge from quantum interactions. No single quantum event has dimensionality. Dimensions appear only when countless quantum processes organize in specific patterns. They're real and important at their level, but they're not fundamental. They're emergent from quantum information. This doesn't diminish dimensions' reality. Temperature is emergent, but heat is real. Waves are emergent, but ocean swells are real. Consciousness is emergent, but thoughts are real. Emergence doesn't mean illusion. It means higher-level organization with properties not present at lower levels. For dimensions, this emergence explains many puzzles. Why do some dimensions stay large while others compactify? Perhaps it's not a choice, but a dynamic process. Certain patterns of quantum organization naturally produce large dimensions. Others don't. We observe three large dimensions because that pattern is stable, self-reinforcing, conducive to complexity. Why does time flow forward? Perhaps because the quantum correlations that create time have a natural arrow, from low entropy to high, from past to future. The direction isn't fundamentally different from spatial directions. It emerges from how quantum states evolve and entangle. Why are there any dimensions at all? Perhaps because quantum information naturally organizes into patterns that we interpret as spatial relationships. Entanglement creates connectivity. Connectivity manifests as space. Space implies dimensions. The reflection on emergence also connects to the earlier theme of holography. If dimensions emerge from information on boundaries, then the bulk dimensions aren't fundamental, they're convenient descriptions of boundary physics. The CFT correspondence makes this precise. 5-dimensional physics emerges from 4-dimensional quantum information. This suggests a picture where reality at the deepest level is just quantum information, abstract, non-spatial, pure possibility. From that information, through entanglement and correlation, space emerges. From space, through special patterns, time emerges. From space-time, through specific structures, matter and forces emerge. Dimensions are features of this emergent space-time, not primary ingredients. This view is still developing. It's not universally accepted. Many physicists still seek fundamental objects and fundamental dimensional structure. But the trend is toward emergence, toward recognizing that what seems basic might be derived. The reflection, then, is recognizing humility. We don't know what's truly fundamental. We might never reach a final layer. Every answer might reveal new questions, new structure beneath. Dimensions might be emergent today and fundamental tomorrow, or vice versa, as our understanding evolves. What matters is that we follow where evidence and mathematics lead, remaining open to radical revisions of what we thought was basic. Dimensions seemed inviolable, clearly 3 spatial, 1 temporal. Then string theory suggested 10. Then M-theory suggested 11. Then dimensional flow suggested the number changes with scale. Then holography suggested they might be projections. Then entanglement suggested they might emerge from information. Each step made the picture more complex but also richer, more connected, more mathematically beautiful. And that beauty, the way different areas of physics weave together, when dimensions are treated as emergent, is itself suggestive. It feels like we're approaching truth, even if we haven't reached it. The reflection is also personal. We live in 4 dimensions experientially. That experience is real and valid, but recognizing it might be emergent, contextual, not absolute, this expands perspective. It shows that reality extends beyond experience, that the universe is stranger and richer than our senses reveal. It's humbling to realize the space you move through, the time you experience, might not be fundamental but constructed emergent patterns from quantum information. But it's also inspiring. It shows how much depth reality has, how far understanding can reach beyond immediate perception. Emergence over fundamentals isn't a conclusion but a working hypothesis. It guides current research, suggesting that instead of seeking irreducible building blocks, we should seek principles of organization, how simpler things combine to produce complex structures, how information organizes to create geometry, how quantum correlations weave space-time. The answer to how many dimensions are there might ultimately be, it depends on scale, on context, on how you organize the information, and that dependency, that emergence, might be the deepest answer possible. Not a number, but a process. Not a fixed structure, but a dynamic becoming. The reflection on emergence also invites reconsidering what we mean by understanding. Traditionally, understanding meant reducing complex phenomena to simpler parts. Water is H2O molecules. Heat is molecular motion. This reductionist approach has been extraordinarily successful. But emergence suggests understanding also requires synthesis, seeing how parts combine to create wholes with new properties. You can't understand wetness by studying individual water molecules. You need to see how billions interact. Similarly, you can't understand space-time by studying individual quantum events. You need to see how countless events correlate and entangle to create geometric structure. This synthetic understanding complements reductionism. Both are necessary. We need to know the parts and how they combine. For dimensions, this means understanding both quantum fundamentals, whatever they are, and emergent geometry, how spacetime arises from them. The reflection is recognizing that physics is moving beyond pure reductionism toward a more holistic view where emergence is as important as fundamentals, where asking, what is it made of, is paired with how does it organize and what emerges. These questions together might finally answer what dimensions really are, and so we return to where we began, having travelled through the dimensions, the ones we know, the ones we suspect, the ones that might emerge from something deeper still. The question was simple: how many dimensions does the universe actually have? But the journey has shown that simplicity is an illusion. The universe doesn't offer simple answers to fundamental questions. Instead, it offers layers, contexts, emergent structures, and mathematical beauty that hints at truths beyond complete understanding. So here, at the end, what can we say? We can say with confidence that at the scales we inhabit, reality has 3 spatial dimensions and 1 of time. This isn't debatable. It's confirmed by every measurement, every observation, every moment of lived experience. You move in 3 directions through space. You flow forward through time. This is the bedrock reality of human existence. We can say that Einstein's relativity revealed these 4 dimensions weave together into space-time, a unified fabric that curves, flexes, and responds to mass and energy. This space-time isn't static backdrop but dynamic participant in cosmic drama. Black holes, gravitational waves, the expanding universe all testify to space-time's reality. We can say that attempts to unify gravity with quantum mechanics to describe the universe at its smallest scales and highest energies seem to require more dimensions. String theory needs 10. M theory needs 11. These aren't arbitrary, but emerge from mathematical consistency requirements. Without the extra dimensions, the equations break down, producing nonsense instead of predictions. We can say these extra dimensions, if real, are hidden, compactified into shapes too small to detect, curled at the Planck scale, or perhaps confining us to a brain while extending invisibly into a bulk we cannot access. The hiding mechanism is elegant and explains why we don't perceive them directly. We can say that holography and entanglement suggest dimensions might not be fundamental but emergent patterns arising from quantum information, from the way reality organizes itself at deeper levels. The number of dimensions might depend on scale, context, how you probe the universe. We can say that despite decades of searching, we haven't directly detected extra dimensions. Every experiment confirming them has failed. Every observation has been consistent with 4-dimensional physics. The constraints grow tighter, the parameter space shrinks, but possibilities remain. We can say that the question itself, how many dimensions, might be more subtle than it appears. Not because we're confused, but because dimensions themselves might be contextual, scale-dependent, emergent rather than fundamental. And we can say that we don't know the final answer. Not yet, perhaps not ever. If the universe proves infinitely layered, each answer revealing deeper questions. But here's what matters most. We can ask the question. We can explore it mathematically, experimentally, philosophically. We can build theories that reach beyond perception. Use mathematics to explore spaces we can't visualize. Design experiments to test what we can't directly see. Human consciousness, arising from matter organized in complex patterns, has achieved something remarkable: the capacity to question its own foundations, to wonder about the structure of reality, to seek understanding beyond immediate experience. Whether the universe has 4 dimensions or 10 or 11 or infinitely many, or none at the deepest level, the fact that we can investigate this question is itself extraordinary. It shows that the universe is comprehensible, that mathematics describes reality, that observation constrains theory, that truth exists and can be approached even if never fully grasped. Living in layered reality means accepting uncertainty while pursuing understanding. It means holding theories provisionally, following evidence wherever it leads, remaining open to surprise. It means recognizing that what seems obviously true, three spatial dimensions, might be approximate, emergent, contextual. It means appreciating that you inhabit a universe far stranger than common sense suggests, where space might have hidden directions folded at every point, where time might emerge from quantum correlations, where the very concepts of where and when might be high-level approximations of deeper, non-spatial, non-temporal structures. This strangeness isn't threatening, it's liberating. It means reality extends beyond what you can touch, see, measure directly. It means there's always more depth, more mystery, more room for discovery. As you drift towards sleep tonight, you can hold this lightly. The room around you exists in 3 dimensions. That's real. But at every point in this room, there might be additional dimensions curled impossibly small, or you might be confined to a brain floating in higher dimensional space, or the dimensions themselves might emerge from quantum entanglement, weaving spacetime from information. All these possibilities remain open. The universe hasn't revealed its deepest structure yet, and that openness is part of the beauty. We live in a cosmos that rewards curiosity, that offers infinite layers for investigation, that never quite runs out of mysteries. The 4 dimensions you navigate every day are enough for living, for loving, for experiencing the richness of existence. But knowing or suspecting that reality might be deeper, that hidden dimensions might surround you, that the space you inhabit might emerge from structures beyond imagination. This adds a layer of wonder to ordinary experience. You're not just in a room, you're in a possibly 10-dimensional space-time, where 6 directions are curled at every point. Or you're on a 3-dimensional brain floating in an 11-dimensional bulk. Or you're a pattern of quantum correlations that has organized into the illusion of spatial extension. Each possibility is strange, beautiful, grounded in serious physics, and not knowing which is true or whether any single answer exists doesn't diminish but enhances the mystery. The closing thought, then, is this. How many dimensions does the universe have? Enough to contain you, to support the existence of stars and galaxies, to allow complexity and consciousness and the capacity to ask questions. Whether that number is 4 or 10 or 11 or scale-dependent or emergent, from something even more fundamental reality is sufficient for wonder. And wonder, in the end, might be what matters most. Not the final answer, but the journey toward it. Not certainty, but exploration. Not knowing, but seeking. The universe doesn't demand you understand it completely. It only invites you to look, to question, to marvel at its depth. And in that invitation, you find your place not as a passive observer, but as an active participant in the cosmos exploring itself. So rest easy. The dimensions will be there tomorrow, whether 4 or more, whether fundamental or emergent, whether revealed or hidden. Your task isn't to solve the mystery tonight, but to hold it gently, to let it settle in your mind like snow falling on a quiet landscape. The universe is vast. Reality is layered. Dimensions weave through everything, visible and invisible, known and unknown. And you are, here, in this moment, part of the pattern, asking questions that reach toward infinity. That's enough. That's everything. Let the questions rest. Let the wonder remain. And as you drift towards sleep, know that the cosmos cradles you in its dimensional structure, whatever that structure ultimately proves to be. The exploration continues tomorrow. For now, simply be. In 3 dimensions, in 4, in 10, in however many the universe actually has. Good night, and thank you for wondering. The closing also acknowledges what we've learned about learning itself. Physics progresses not in straight lines, but through revolutions, paradigm shifts where basic assumptions are overturned. Newton's absolute space and time gave way to Einstein's spacetime. Classical determinism gave way to quantum probability. 4 dimensions might give way to 10 or 11 or emergence from information. Each shift felt radical at the time but became natural in retrospect. We're living through such a shift now, where dimensions themselves so basic, so obvious, are being reconsidered from foundations. Future generations might look back and wonder why it took us so long to see that dimensions were emergent, or contextual, or scale-dependent. Or they might return to 4 as fundamental after all, finding that extra dimensions were mathematical scaffolding, not physical reality. We don't know. We can't know from where we stand, but we can participate in the exploration, contributing our piece to the larger story, and we can hold uncertainty with grace, recognizing that not knowing is not failure but the natural state of frontier inquiry. The universe reveals itself slowly, layer by layer, dimension by dimension. And we're here, watching the revelation unfold, part of the cosmos awakening to itself. That's the true closing, not an answer, but a position, curious, humble, engaged, wondering. Living in layered reality, exploring dimensions seen and unseen, asking questions that may not have single answers, but that deepen understanding with every attempt. This is what it means to be human in a mysterious universe, and it's enough.